welcome to today's session, the first of our mini courses for this workshop. This mini course is on deep neural network robustness, and it will be run primarily by Bernard Ghanem, and I'm going to massacre these names: Motasem Alfarra, Hassan Hamoud, and Juan Perez. I did pretty well, I think. I only have an introduction set up for the PI, Bernard. I'm sorry for the other guys. So this is going to be 4 sessions of 90 minutes each, and the first one is presented by Professor Bernard Ghanem, who's now full professor in EC and computer science here at KAUST. He's also the deputy director for the AI initiative here at KAUST. He did his PhD in Illinois at Urbana-Champaign, and did postdocs at UCN in Singapore, and is now head of the Image and Video Understanding Lab. And he's going to present the first session. So please take it away, Bernard.
All right, thank you, AJ. Is audio fine? Are people in the back hearing me? All right, great. So good morning. It's early morning for me, so excuse the grogginess. We have a conference deadline tonight, and it was a late night last night. So excuse any mistakes or whatever that I say during this first hour and a half. The session that we're going to be running today, all 4 parts of it, they're going to be about this particular topic of the robustness of deep neural networks. So who here has not heard of what a neural network is or a deep neural network is? Who has not heard of it? Okay, that's great. So that means we're all on the same page. So we understand that this revolution of AI that we're currently, or this era of awesome AI stuff that's happening nowadays, to a good extent, it's because of the tools that are being used, and these tools are deep neural networks of all kinds and shapes, and there's been advancements in how we train them, what kind of data sets we use to train them, how to optimize for them, what kind of architectures to use. There's a huge literature on this, and it's in a very exciting time to live in right now. My lab, the one that has this awesome logo right here, all right? So it's the evil lab. We all do good stuff there. Nothing evil or nefarious, but it's pronounced in the French way, evil. So in my lab, we do a lot of computer vision. So mostly it's about applications or development of neural networks, especially, or machine learning techniques in general, on visual data. So recognizing what's in an image. Can you name for me what kind of objects there are in this image? Where are these objects? What are people doing in videos? So forth and so on. So these types of examples are what we tackle. These particular really cool, exciting applications, let me give an example of them right here. Okay, I guess I have to click. Okay, I can do it now. All right, so here's examples. On the left, for example, you have detection and classification. So basically, you want to generate a bounding box around objects and name what these objects are: cars, pedestrians, poles, where the road is, and so forth. On the right, same thing, but it's a segmentation problem where every single pixel in the image is labeled with a color depending on what its semantic class is: road, cars, pedestrians, trees, buildings. The reason why that's in 2D and in 3D, one application of this obviously is in self-driving cars, right? So the car needs to know what's in front of it, whether there's a pedestrian or just empty road, right? Because that will determine whether it will go right through or stop. So the deep neural networks that are being trained to do these exciting applications are doing very well. So you see examples of self-driving cars actually running around and driving around by themselves in many, many cases very successfully and getting better by the day. This is just one of the many, many examples of the new AI era that we live in. Other examples are in other application fields, like in medical image analysis, diagnosis of diseases, social media tools that allow you to filter your face or add interesting properties to your face or to your TikTok videos. All of these things use very similar backends, which are these deep neural networks. Here are more and more examples. If you wanted to know when in a video LeBron James dunk the basketball in an automated way without doing it manually. You can do this. If you wanted to track where tennis players are going and how they're hitting the ball, or you want to train in an automated system to play an online game and beat champions in that game, or you want to train a car to drive in unseen scenarios, just like this one over here. So many examples of success stories. You have deep networks being deployed on your phones. If you use any kind of Google translation or any kind of translation services, if you use Siri or Iris or Google or any of your smart assistants, you're using these deep networks also. That's all in good, but there are issues. These 4 sessions are going to be about the robustness of these models. They do very well. They're being integrated into commercial products. We're using them in our daily lives. They exist on the rover that was sent to Mars, that is flying, that is running around on, by itself, and as well as the UAV that's on Mars. All of this is great. However, how robust are these models? I don't know if anybody here has seen such examples where you take an image of this pig, for example. We have other examples of other animals, obviously. If you take a picture of this pig, you pass it through your deep neural network that has great accuracy, it tells you this is a pig, okay? It does classification very well. You add a little bit of noise, and this little bit of noise is very imperceptible to the human eye. So for example, this is the noisy version of this. I think we all agree that this looks almost exactly the same, if not exactly the same. And yet that image, you push it through the same neural network, it tells you this is an airliner. Completely wrong prediction, completely wrong. And not only that, you can actually, it turns out you can tailor what this noise is so that this thing that you predict could be anything you want. This is bad, right? Obviously, this is very bad. Now, why should we care? Why should we bother? Because who cares about this additive noise that you add to an image and it could flip that image to any other class? Because this additive noise maybe is not really natural. Well, look at this example. You have an image. This is a video. You're applying a deep neural network per frame, per image. And when you take out this piece, right, it tells you that it's a banana with very high confidence. Once you add that little piece, that adversary, now no longer a banana, it's a toaster. And obviously this is bad for us, right? This is not what we want it to be. We want it to be robust to these particular attacks or these particular perturbations to the input space. More and more examples. This is a great example about from 2019, where actually Tencent AI Lab, they looked at the autopilot system on the Tesla car. What they did, I don't know if it's visible really from back there, but they put in the physical world, they put white stickers on the roads, a few of them. And all of a sudden, right, this was determined as a lane. And once it's a lane, then the navigation system makes a decision, and the autopilot of the Tesla car went haywire. So this is a real world attack. So imagine somebody going around and putting white stickers on roads, your Teslas start crashing into people and crashing into buildings. This is not something that we want, right? Obviously. So the robustness of these networks is not only a theoretical or a mathematical exercise that we do to make these networks more stable mathematically, but it has real world implications. So in this mini course today, we're going to be talking about various aspects of this particular thing. What kind of attacks are there? How can you perturb the network or the input of the network so that it breaks? How do you defend against these attacks? How do you make the networks robust? What types of robustness are there out there? How do you certify that there does not exist a perturbation? Can you train a network in such a way that you can give a certificate, a guarantee that there will not be an attack that will flip the prediction of the network? in addition to different various types of attacks, among them being backdoor attacks, and we're going to be talking about that in the afternoon also. So this is how it's structured. We're not going to be talking about how to making these deep networks higher, more efficient or higher performance. We're talking about its robustness, their stability, and their applicability into the real world by making them less sensitive to perturbations of various types. So again, why are we bothering? Because these perturbations or attacks could happen in nature. For example, the same neural network that predicted this is a revolver, which is a correct prediction, right? If you rotate it or apply a particular spatial transformation to it, you get something like a mousetrap. This does not look like a mousetrap, right? So this is not a simple additive perturbation to the input. This is a kind of a spatial transformation, which is more real world. Same thing goes with a vulture that became an orangutan. How about more real world stuff? This is, I mean, the field is getting really interesting. These are papers that are showing these great demos actually, and they show you really how people are trying to break deep systems built on deep networks. So this person is, we're looking here at the task of tracking. That means finding where this person is, where the person walking is throughout the video. So you see a bounding box around the person, and you want that bounding box in green to stick onto the person, right? That's called tracking. Now, the interesting thing here is that this person, knowing that he's being tracked, will put up some kind of a poster. So people in the field are actually synthesizing posters, particularly, knowing what kind of deep neural networks are being applied in the real world, a particular poster such that if that poster exists in the actual scene, the tracker gets confused and starts tracking that poster, and this person can do whatever they want. They're no longer tracked. Same thing goes over here, and this is where, this is more of a synthetic kind of example. But this goes to show you that you can have real world attacks which make you kind of invisible to these. Any kind of surveillance system is built on deep neural networks if they can be attacked in the real world without being hacked into, but by maybe you wearing some particular type of t-shirt with a particular type of pattern on your t-shirt or on your head or somewhere else in the scene that distracts such surveillance system. So these are things that we need to definitely worry about. And the question is, what kind of attacks are these? How do we make the neural networks robust against them so that this doesn't happen? We go back to it. So the premise of network robustness is that I want a neural network, a parametric function f, that if I give it this image input, I get this label. But also if I give this noisy version of this input, I get the same label. That's basically what stability or robustness is for us. Okay, so this is how the outline is going to be structured after that really long intro. I hope it's very well motivated and you're excited for the day and excited for the next 6 hours, I guess, 6 hours. So we're going to be talking about, so I'm going to be giving the overview, the high level motivation of how cool the field is. But then the real stuff is going to be coming later. So later this morning, so my student Motasem will be talking about certification. These are theoretically guaranteed mechanisms to make these networks not foolable. Okay, so these are guarantees. And so it's really interesting theories. So something about randomized smoothing, many things about randomized smoothing as a technique will be discussed. Then in the afternoon, my other PhD student Juan Camilo Perez will be talking about realistic perturbations, so semantic perturbations. For example, he will give a great example of let's say you want to break into a face recognition system. Okay, let's say there's one at the gates of KAUST, right? When you go in, it scans your face, it knows who you are. It does very, very well. If you had that kind of model of recognition, can you come up with a semantically meaningful perturbation of your face that could prevent that system from recognizing you correctly? For example, changing your hair, adding on glasses or different types of glasses, smiling in a particular way. These are semantic perturbations. You can actually move your face and change these features of your face such that this is possible. So perturbations in the real world are realistic perturbations that can actually break systems. These are very interesting. We're going to talk about them in the afternoon. And then in the second session of the afternoon, my other PhD student, Hassan, will be talking about backdoor attacks. And this is really scary. This is really scary for all of you who are wanting to train deep neural networks, especially based on data that's not yours, something that's pre-trained, or data that's yours but you have somebody else training it for you. Something very, very scary. So they're going to be implanting backdoor attacks into your network that you think this neural network is doing great, it's doing fine, it's a perfect neural network, and then all of a sudden this attacker that embedded this backdoor attack is able to use the backdoor to do some nefarious things. So it's a very scary thing out there, and Hassan will be talking about this in the afternoon. All right, so of course, if anybody has any questions at any time, please raise your hand and we can discuss. The purpose of this course is to kind of convey some information and make sure that you guys are aware, you guys and gals are aware of the literature and the interesting works that are out there. And if you have any questions, maybe about any of the content, just raise your hand and we'll be happy to answer those. All right. So having given that long-winded introduction and motivation, let's get right into it. So when we talk about attacks or adversarial attacks, so these are attacks that are trying to fool the system in some way or another, okay? There's two main types of adversarial attacks. You can attack the network in training, during training, and this part of this will be included in the afternoon with Hassan about backdoor attacks, where you actually the attacks are not while you're doing the training of the network, the attacks on the training data or how the network is being trained is being conducted. Okay, so this is during training time. That means the network hasn't been trained yet. How do you add adversaries? How do you defend against these adversaries? Now, this is the training time attacks were they're more recent in their development. The more established type of adversarial attack are these inference time attacks. This is exactly what I talked to you about when you looked at that pig image or the person who's evading the tracker image. That means the network has been trained by an expert. All is good there. There's no nefariousness or adversary trying to that has affected the training there. That's all good and fine. But at inference time, that means if you give this network that's already been trained an image to infer on, to predict on, that's where the attacks happen. Okay, so there's two types of attacks, and there's going to be defenses on this. So, for example, here you have inputs of, let's say this is a neural network that takes as input images. You'll take images as input and it predicts labels, let's say human face. What kind of attacks can you do on the images of the input of this network that's already been trained? Okay, so we'll be focusing for the most part on these inference time attacks, but in the afternoon, Hassan will talk about some training time attacks. There's this phrase that is used in the literature called the model threat or the threat model. So basically, it's like, how do you model what an adversary is, all right, mathematically speaking? You have to model it in some way. Otherwise, it's not clear how are you going to attack, how are you going to create the attack, and how are you going to defend against it if you don't have a model of what this threat looks like. Well, we've seen this before, right? This additive perturbation, that means you have image X plus perturbation delta, okay? Simple, right? You start with the simplest thing, which is additive perturbation. This is not as realistic, right, as many, well, not realistic in general, to be honest. This is why, although the theory here that's being built is very intricate, the reason being this model, threat model, this additive threat model is easy to handle theoretically. Other more realistic but harder types of threat models that are to analyze are these kind of transformations. For example, rotations, homographies, translations, crops, and so forth. These are more semantically meaningful than additive noise. They're harder to analyze. And then there's the more semantic ones, which are basically you have an image of a person. This is the example that I told you that you're going to see in the afternoon. You have an example of a person, and then she takes her glasses off and changes the smile a bit and maybe a little bit of her hair. By the way, this is fake. So this is a real person. This is the fake generation of what would she look like without glasses and different smile. This is generated by a GAN, by the way. It looks very realistic, doesn't it? Yeah. So basically, this is a fake version of her, or one of the other way. I forget. One of them is fake. Either we add glasses and change the smile. Anyway, but let's say this is the real one. This is the fake one. Fake version of it, of what would happen without the glasses and change of smile. This going to a deep network that does face recognition would say this person is no longer the same identity. All right. So these are very semantic, realistic perturbations, right? This is something you can do. You can take off your glasses. You can smile differently. You can change the color of your eyes by putting these colored contact lenses. These are things you can do in the real world to break the system. So obviously, there's more theory and interesting properties on this side, since it's a simpler model to handle. But we are trying to, I mean, my lab, especially, that we're working on all different types so that we have a good diversity of, good theory as well as things that work in the real world. This is the simplest mathematical formulation, therefore it's more cohesive to more interesting properties mathematically. Yes. Yes. But you will see that this is not random. You'll see that these attacks, these perturbations will be designed in a certain way. They're not going to be random. They're going to be dependent on what X is. They'll be dependent on what the image is that you're trying to attack. Yeah. Say it again. Mm-hmm. I mean, there are augmentation methods actually that have these that add random perturbations to allow for better generalizability of neural networks already. But what we're talking about here is that randomness or perturbations that have a particular goal of beating the system, fooling the system. But of course, I'd love to talk to, I always love to talk to Raoul about all these various things. And we have a CRG ongoing for this particular reason. Yes, definitely. It's an exciting field. And this is why, I mean, this course and you in the audience, I mean, you could be looking at these problems from a different viewpoint, from a more mathematical, numeric, stochasticity point of view that could add more flavor or even more insights on what the problem is. This is why we're interested in presenting all this work to you. All right, so we need to formalize this mathematically. All this great stuff that I've been pitching to you, we need to formalize this mathematically to figure out how do we generate attacks and how do we defend against them, right? Simple as that. All right, so there are two main things that you need to be careful of or be aware of in producing or generating or learning what these attacks should be. They should fool the network. What does that mean mathematically? Okay, that's one thing. Another thing is they should preserve semantics, meaning I want to perturb let's say you're talking about image classification where your deep neural network takes as input an image. Okay, let's say, for example, an image of a cat. Okay, takes it as input, it outputs a label called cat. All right. So, and I'm going to allow, let's say, additive perturbation. I'm going to add to that cat image something that once I add it and I push it through as a forward pass to the neural network, it should output something that's not cat. The adversary is interested in fooling the system. So I wanted to predict something that is not cat, right? However, you need to constrain this hacker that's adding this perturbation, because they could add so much noise to the input that that actual noisy version of the cat image is no longer a cat. You don't recognize it anymore. So this is why this kind of preserving semantics means that you cannot add too much perturbation so that the semantics of the actual image has changed. So it's no longer a cat, it's something totally different after you add the perturbation. So think of it as the first part here is going to be like a loss function. This is going to be a hard constraint and an optimization. This is what we're going to be doing. So this is exactly it. So let's say this is the pig image over here. This is the decision boundary between two classes, C1 and C2. C1 could be pig, C2 could be not pig. Okay, this is a decision boundary between them. What I want to do basically, and this decision boundary is a byproduct of this deep neural network, parameterized deep neural network called F. Okay, it generates this decision boundary whereby if you're on this side of the decision boundary, you're labeled as C1. If you're on this side, you're labeled as C2. This is how supervised machine learning works, right? Now this is where the pig image is, and the idea is that I want to find a direction and a magnitude whereby I want to shift this x, this original x, so that it used to be C1. I want to shift it into, I want to fool it, right? That means I want to flip its label from C1 to not C1, which is C2. So I want to move it from here to here. Of course, if you went along this direction or this direction or this direction, you're still going to stay within the C1 region. These are bad directions to fool the network. I want to flip it over to the other side. All right, that's all. That's what we mean by fooling, right? So what is the direction? How do you what kind of vector do you add to x so that you push it from here to here? And the way to evaluate whether it's being pushed is how good is the prediction? That means if you added a delta perturbation to x, is the prediction of the network f on the perturbed version of x, I want it to be different from the actual ground truth label of x. So here x, its ground truth label is C1, but I want f of x plus delta, right, to be C2, something different than C1, right? So this is kind of the very simple idea of additive attacks. Here's a nice visual version of that. So you have the input to be x, this is a panda. It goes through a deep neural network in black. The reason why we drew it this way, because think of it as a black box, right? But it's parameterized black box. You don't need to know what's in there. You know, architectures, how it looks like, how many parameters. That's irrelevant to you in this course. All what you care about is that there's function, it's differentiable, it has parameters theta, and it generates a function f. Okay, it's like a prediction. So x is the input. F of x would be a vector of k values, the largest value of which tells you which label this thing is. So for example, let's say you have 1,000 object classes, k is 1,000. This neural network will output a vector of 1,000 dimensions, one for every object class, right? They all sum to 1, and all these values are from 0 to 1, right? So it's like it's on the simplex, right, of 1,000 dimensions. And so this input image x goes in, and the output would be a 1,000-dimensional vector where the panda element in this 1,000-dimensional vector would be very high because this is actually a panda, right? So that's all good. What about if I want to want to measure how good this prediction is? F of x is the prediction of the neural network on the input image x. I want to measure how good it is with respect to the actual ground truth label of this image. Call it y. Somebody gave you what y is. For example, humans have labeled that this image is a panda. All right. So this loss function of between the prediction and the ground truth label, this loss function could be whatever you want, right? You could pick whatever you want, but usually it's something like cross entropy, because you want to compare a PMF to another PMF. So you use cross entropy to tell you how quantitatively how close the prediction is to the ground truth. All right, that's great. Now the question is, usually when we train a neural network on a training set, you have images and you have ground truth labels. You want to train the parameters of this big black box such that the prediction of the neural network and the ground truth are close. So we want to try to minimize the loss of the prediction between the prediction and the ground truth on all the training samples. This is what we do in training. But in adversarial attacks, you're an adversary, you're a nefarious person. What do you want to do? I want to maximize the loss between f of x plus the perturbation and the ground truth label y. I want to maximize it because I want to try to, force you to make an error, and you're forced to make an error if you maximize the loss. You're saying make the prediction of the neural network and the ground truth label be as far apart as possible from each other. Yes, definitely. Right. Great. We call that in literature targeted attacks. So there are two types. We're not going to go into that much detail here. There's two main types of attack. Untargeted attacks, meaning I want, like this, maximize the difference. Meaning go from Y to not Y, whatever it is. What you're describing is a more difficult attack, because how about if the actual, here in that example of C1, C2, they're close to each other, but in this high dimensional decision boundary thing, it could be very, very far away. And you might not be able to reach it within, because remember, we have some constraints on how much you can move, right? So, but what you're talking about is targeted attacks, meaning I want to make the loss between f of x plus delta to the target y, yt, to be minimized, right? So you want to get it as close as possible. That's exactly it. It's called targeted attacks. And both are valuable. All right, so mathematically speaking, this is an optimization. I want to maximize, if I want to fool the network, that means flip the label. Not flip it to a particular target, but flip the label in general. I want to add perturbation delta to the input x, such that with a trained network f, that means the network has already been trained, I know its parameters, such that you maximize this loss. Now, obviously, this has issues because if you just solve this type of optimization, you put no constraints on what delta should be, right? That means you can add as much noise as you want. You can totally ruin what x is. That's not what we want. We want to preserve semantics. So we're going to put some kind of constraint, semantic constraint. And for all intents and purposes, we want to make it simple. So let's say a p norm on delta has to be bounded. This p norm could be infinity norm, 1 norm, 2 norm, whatever. We keep it simple to make the attack mathematically simpler, right? Of course, there's innovations in the literature on how to formulate this fooling of the network, how to formulate the semantics, how to solve this optimization. There's been a lot of papers exactly on this topic. All right, so we need to stay within this LP ball, this semantic space. And so projecting onto it, depending on the P. So for infinity ball, for P equals to infinity and to 1 and 2, or to these two, 2 and infinity, there's a closed form solution of how to project onto these balls. Very, very easy stuff. So in many cases in the literature, you see that P is taken to be 2 or infinity. Okay, so you project onto that space. The projection onto that space is, onto that constraint space is very simple closed form projection. So how do we make use of that? Well, I want to find this attack. That means I want to find what delta is. I start with delta all zeros, let's say, and I want to solve this optimization. This is in general, F is a neural network. It is a very nonlinear, non-convex function on the input x, therefore on the input delta. And so this objective of the optimization is not nice, okay? As well as the constraints are easy. I mean, the P is usually taken to be infinity or 2 norm, so this is a convex set. So the projection onto it is easy. So how would you, if I were to give you such an optimization problem, the first thought you would have is, I will solve it using projected gradient descent. I'm sure a lot of people here have heard of gradient descent, right? So you want to minimize or maximize, let's say minimize an objective function without constraints. What do? You follow the direction of the negative of the gradient, right? The certain step size. You keep on doing that until converge. You guys, I'm sure, are aware of that. So how about if you had hard constraint? And that hard constraint is easily projectable onto. You can project onto it. So projected gradient descent. So you start with, let's say p equals to 1 is this kind of space. P equals to 2 is a circle in 2D. Infinity is this ball. And this is the space you want to project onto. Okay, you can't get outside that region. So how does PGD work? Well, you start with x. You go along the direction of the gradient. We're trying to maximize here. So it's not negative gradient. We're trying to maximize. Therefore, we go along the direction of the gradient of L, the loss, with a step size alpha that might go outside your constraint space. And so you project back. That's the first iteration. Then now you begin the second iteration, do the same thing, project back. Do the same thing, project back, and do the same thing, project back. Okay, that's what PGD is. Very simple. It maintains that at every iteration, you're always within the constraint space, right? So that's good. And it tries to decrease this objective. Of course, again, in the literature, there's many works that try to improve this, make this more efficient, blah, blah, blah. So this is not the only method to solve this optimization, obviously. But keep in mind, you'll see it later, we don't want to spend a day to create the best attack for this one image. Why? Because later when we talk about defenses, meaning I want to defend against these attacks, I will defend against these attacks by creating them on the fly on many, many, many training images, right? Or training samples. So that means if it takes me a day to create one attack by solving this optimization, it's not going to be scalable for me to actually create a defense in any reasonable time. Okay, so there is a trade-off. There is a need for creating a solution or finding a solution or an approximate solution to this optimization in an efficient manner. So those of you who are interested in solving things or doing some more efficient optimization methods, this is definitely a problem that's interesting to the community, and there's been many, many works on this. Yes, Khalil, right? Shihab. Well, once we get to defenses, you'll see more. There's many different types of defenses also out there. But usually an empirical defense is a defense against a particular type of adversary. So you remember we talked about a threat model. What's the perturbation? It's additive, let's say x plus delta creates the perturbation. You would defend against that type. But like I said, the additive perturbations are not the only type of perturbations. How about instead of x plus delta, how about spatial transformation of x? Remember, the rotation, where there is a parameterization of how much you rotate, translate, crop. What about functions on x or more complicated functions on x instead of just x plus delta? So depending on what kind of threat model you have, you usually have a defense against it. These are empirical defenses. And then Motasem is going to talk about certification. That means no matter what the threat model is, you're guaranteed that there does not exist an adversary of that form. Yes, Rahul. Yeah. Yeah, this is why the field is evolving, and there's much work still to be done. So the problem with making the constraint space more complicated is that you end up not being able to do PGD. The optimization becomes much, much more difficult. And what kind of modeling do you do? So for example, instead of, like, say the threat model is x plus delta, right? That's the perturbation. And I want to bound the difference in energy between x and x plus delta. That gives rise to this kind of constraint space, right? If you want to make it more difficult, it can get more difficult. And therefore, all of this generating just one adversary becomes much, much more difficult. People are working on this. It's very important to be able to create attacks that are semantic, but that will create more complexity in what this constraint space is. It's a trade-off. But yeah, we want to get to more semantically meaningful perturbations, but in such a way that we actually can find them in an efficient way, because as you'll see in the defenses, we need to create many, many, many of these in training. So yeah, there's a lot of interesting room for improvement for sure. And anybody who has good ideas about how to make things more efficient or come up with better solvers, faster solvers, it'll all benefit the field. PGD is a typical way of solving these things with these particular threat models, with these particular constraint sets, right? So this is why the literature, at least the initial literature, has proposed using these semantic constraints because they're easy to project upon. It makes the steps easier to do. All right, so till now, what kind of, does anybody have questions that I can resolve? Yes. No, but if the so this sample, its ground truth is dog, you're saying? The ground truth label is dog. It does. No. This is what. So remember, I told you that there's this k-dimensional output. It outputs a PMF of k bins. K meaning being the number of classes. Every value in this k-dimensional vector is from 0 to 1 and sums to 1. So it's an actual PMF. And so, is that what he means, or? Yeah, I see. That is true. That is true. Okay. So that's a good point. Thresholding is a good point. Keep in mind that, so that's great. So the more realistic you make the setup, the optimization, the more difficult it is to optimize for it. Simple as that. So this is why we're maximizing the loss between f of x, which is this PMF, and the ground truth. We're not guaranteeing. We don't want to make sure, we want to just maximize the loss. But even if you had the best optimizer and you found the maximum loss, the prediction might still be y, might still be the ground truth, no matter what you do, right? So the best thing that we could do is to maximize the prediction between the soft output, this PMF, and the ground truth PMF, right? So we're not doing thresholding, right? Because we're aware of that, but if you're able to maximize it, if the maximum loss doesn't get you to, if you thresholded that f of x was delta at the maximum loss and it's still y, that means you cannot break the sample, no matter what you do, right? I mean, this is we can agree upon that. So this is how we skirt away from this idea of thresholding this PMF from f of x. No, the crisp answer is the max. Yeah. No, as you'll see, I mean, it's not, because all the f of x is not actually a thresholded PMF. It's the PMF. The f of x is the PMF. It's not the thresholded PMF. Yeah. So the boundaries are where the hardness comes in. So this the decision boundaries are the following here, right? Yeah, exactly. So any x in this realm, right? So f of x in this case would be two-dimensional, right? So you have one value for C1, one value for C2. If the value of C1 is larger than that of C2, you should be on this region. Larger only. That means if you had thresholded, you would have picked C1. But you see, if you had thresholded, this is where the boundary comes in, right? But that means, but every element here, right? It's F output, the PMF output of F for C1 has its value is greater than that of C2. So we're F outputs and a PMF, a soft. So it's not thresholded. It's soft. The F is soft. to create the final label, to make a decision. Yeah, but okay. So true. We want to cross the decision boundary, so we want the thresholded prediction to be wrong, right? To be in the other space. From an optimization point of view, it's much harder because then you would have to factor in this thresholding. But right now with this loss, when I say loss, it means some kind of a differentiable loss cross entropy. This F is the PMF output. So it's smooth in the thing. And Y is the ground truth. So this thing, at least I can handle, I can find the first order gradient. This is what, no, I'm saying you're right. I mean, ideally it should be that I want to the thresholded version of the PMF of F should be very different from Y, right? But optimizing that would be difficult. So the surrogate is to do this. It's true. All right, great. So again, PGD is not the only thing out there. You could do other interesting things to optimize for this, but it gives you kind of an idea of what an attack means. An attack is basically a solution to this constraint optimization that's been set up and modeled in a very simplistic way. It might not represent the real world, but it's at least something, right? And people are developing more and more interesting models of the threat and how to solve it and using that in defenses. Yes? You mean rotate the input? You mean the X, rotate the input X? Yeah, the threat model could be different. This is what I'm saying. So this threat model here, X plus delta is your threat model. So imagine that instead of having an additive perturbation, it's a much more complicated function than X. Let's say rotation, translation, or whatnot. Yeah, but what is the right norm? I mean, it doesn't even have to be a norm. All models are wrong, some are useful, right? So I would stick to that statement. Yeah, you need to start somewhere. And I mean, there's innovations here, what this should be to make it more semantically meaningful. There's perturbations, there's advancements in what the threat model should look like and how to optimize for this whole thing. So people are working on various parts of this. This is kind of the most simplistic thing that you can have. So if you change the threat model, this X plus delta will change to the threat model that you use. So it's not additive, it's something more complicated. If you want something more semantic, this will have to change. But currently in the literature, I mean, this is the most popular formulation for the problem. There are innovations. This is not the end thing. I mean, this is a field that's evolving. So we have innovations every month, actually, even sometimes faster. Any other questions? So the key message that I want to bring to you is that generating an attack, finding an attack, this perturbation delta is a solution to some kind of optimization that has to do with a loss that tells you how different your prediction is to the ground truth class, and some semantic constraints that can be represented in the simple way of a p-norm. So solving that will give you an attack. Do you need to solve it? Do you need to get a global solution to be able to generate the attack? That's not necessarily true. This PGD way of optimizing this constraint optimization, it doesn't necessarily guarantee any kind of global optimality, right? Obviously, but in most cases, it's pretty good. And you'll see. I mean, I'm putting a lot of effort onto this, but you'll see when we get to defenses, how we defend against attacks. You'll see that this is a module in a bigger system, right? And so, of course, there's been work on making this more complicated, more realistic, but also if you want to plug this in as a module inside this bigger system, it has to be efficient, and therefore maybe in many cases, maybe making it more simpler would be a better way forward. Yes. So okay, when we get to the different types of two types of robustness, empirical robustness and certified robustness, your argument is on the empirical side, empirical robustness, and it's a cyclic thing. So every time there's an attack, the defense that defends against it, and then once that defense is out there, you have an attack that breaks that thing, and it's a cyclic thing. And you'll see that this is how I'm going to end the first session. There was a paper that I'm bearing the lead here, but that's fine. There was a paper that iClear is a well-known machine learning conference. There was a paper that there was like nine different papers on different attacks, right? Because it's a very attractive field. There's lots of papers. And so these papers were published onto arXiv before the actually conference happened. And by the time of the conference, there was a defense that broke all of them. And the other way around, right? So there's defenses that, so things are evolving, it's cyclic. That's empirical robustness, where you define a threat model and then the defense based on that threat model. But certified robustness, this is what Motasem was talking about, is that no matter what threat model you choose, right? Or at least for a particular threat model, there does not exist an adversary. There does not exist. You cannot find one theoretically guaranteed for that particular threat model, right? So, so that's why there's empirical robustness and then there's certified robustness, and we'll get to that in a bit. Yes.
Yeah. So could you have like one neural network that you train to try to attack, and then the other one tries to
a different one?
Yes, tries to find is this an attack or not, and classify this as attack or not. So they fight against.
I've seen papers that try to do that. Yes. Yes. So think of like a GAN, like our min-max problems, where you have somebody. Actually, what do GAN stand for? Like a GAN, it's an abbreviation for generative adversarial attacks. The generator is trying to fool the discriminator, and vice versa. So people have been trying to do that. Yes. So instead of solving optimization, you have a network that produces this attack. Yes, exactly. Great. All right. So what is robustness? I think I buried the lead when I talked about robustness and defenses without actually defining it. So what is robustness? Well, what I want is for this not to happen, right? That's basically it. I want to train my network. So before, what we had is the setup was I have a deep neural network. I have an input, break it, okay? Now, the network has never been made aware that such attacks exist, right? So that's the problem. It was never made aware during training that somebody's trying to break into it. So how can we robustify? How do we make the neural network itself robust? What do we do? What can we do in training to secure that property? Well, so this is well, it's the same thing that we saw before. Basically, solving this constraint optimization for delta in this constraint space, it will give you the worst case attack. Meaning this, if you could find the global solution to this maximization problem, this is the one that breaks the network the most, right? This is the worst case scenario. Great. So how do we incorporate that in training? Well, the classifier is something that outputs, again, this is it outputs to the space of PMFs of a certain size. So our N is, it could be an image, it could be two-dimensional, but it doesn't matter. So let's say it's n-dimensional to this PMF of a certain size. And the perturbation region is, for example, defined here. In this case, is that P is equal to 2 with a 2-ball. So we say that F is robust against perturbations from this set delta at X if the argmax, this is going back to Raoul's point about whether it flipped to the other side or not. The argmax of Fi of X, because F is a PMF, the location of the max, right? So that means the one with the class that has the highest output, right? That's usually the one that we use for the labeling, is equal to the argmax of this perturb prediction. That means you perturb the input X, you push it to the network, you look at the PMF output. If the maximum exists in the same location as that of the unperturbed, the clean image, then this thing is robust, right? Your network F is robust because you couldn't fool it. Subject to delta, which solves that optimization that we had before, that's in this range that's in this range over here. Okay. For any, by the way, sorry. So this is not for a particular. This is for any small delta in the set delta. Okay. So this is why for every delta in delta, this is certified robustness. That means no matter where you are in this circle, no matter what point you pick, this will always be the case. That means you cannot flip the label here. This is certified robustness. It's a much harder condition to prove, and Motasem will be talking about that after me. So how to check for robustness? Well, you solve for, what you could do is solve for the worst case perturbation, which is solving this maximization problem, which is complicated. Say the solution is delta star. Well, let's say you could solve it and check this thing, right? If the worst case scenario satisfies this, then you should be okay, right? So this is how you can check, and this is called certified robustness. That means if this is the case, there does not exist an adversary in the delta set, the LP ball, around X that flips the prediction of the network. So I want to train F in such a way that this is satisfied. All right, that's how I make it robust. Yes. Certified. This is why, I mean, to certify, so you mean for whatever X is, you mean? Or for whatever delta is? Wait, what do you mean probability? For delta or for X? For all X or for all delta? Okay, so for all, so that's a good point. For all delta, if you want to guarantee this for all delta, this is called certified robustness. That means the network that you just trained has a certificate. It comes with a certificate. You cannot break me at this point. Now, if you want, if it's not 100%, it becomes 90, 80, whatever, then it becomes more like empirical robustness where you cannot guarantee. But of course, the higher the percentage, the better, the more certifiable this network is. So that's the difference between certified robustness and what we call empirical robustness, where you cannot guarantee this fact for every delta in set delta. Yeah. Now, of course, I want to do this also. I mean, I'm training the network, so I want this property to be at every single X also, right? So that's even, so imagine you have a data set of a billion images. You want this to be true everywhere at all the X's. We're not looking at one X anymore. We're trying to train F. We're trying to find a property that we want in the network so that we can satisfy it during training of F. Imagine that, right? So of course, this certified robustness is a much harder problem than empirical robustness, where you don't want it to be certifiable against 100% or robust against 100% of these samples, but as much as you can get. All right, so this problem, the problem is here. So this is certified robustness, So the problem is solving this particular problem, this optimization. It's very difficult because we want to get the worst case, right? So that means we need to find delta star. This is usually very difficult to do. Actually, if F is a neural network that's deep, it doesn't have to be that deep, but deep, and if it's used these particular activations, these rectified linear units, which are piecewise linear, then you could to find this delta star, to find the actual delta star. People have used many different types of methods, mixed integer linear programs, SMTs, whatever, but these methods have been shown to work on very tiny neural networks, not realistic. It's super expensive. And by the way, this is only to find one, the worst case for one example X. Remember, we're trying to incorporate this into the training of a deep neural network. There's going to be millions of X. So if I need to set up a mixed integer problem that takes me, I don't know, hours at the best to find one worst case adversary, this is a problem, right? So these methods do not scale to the problems that we're at, like ResNet 50, which is, to be honest, by our from where we stand, this is actually a small network. It's not, I mean, we're talking about, we're in the era of models that have billions, and I hear that there's also trillion parameter networks. So this thing is very small in comparison, right? So it's not going to be able to, so applying these kind of problems to find the actual global solution will take too long. So of course, there's innovation on this end also, but since you want to find the best, the worst case perturbation, it's very difficult, but there is still advancements on this end, and people are trying to expedite the way to get these global solutions. But if you could get it in a very efficient way, you want to be able to enforce this constraint in training. So of course, if you could find the solution in an efficient manner, this would be great. But unfortunately, that's usually not the case. So it doesn't scale to large networks or large data sets when you use it for defenses, but it provides guarantees. This is the worst case perturbation. Now, we need to approximate this. So instead of doing certified robustness, which is you guarantee this constraint for every delta, how about we guarantee it at 1 point? Right? So, instead of this whole set, 1 point is fine. But that point is picked in a smart way. It's picked to be such that it kind of solves this, right? Not necessarily the global solution, because that's going to take forever. Something that is kind of or close, or whatever you want to call it. The best thing that you at your disposal to try to maximize this objective, and guarantee that this is equal to this at that point alone. Okay, that's a good way to to approximate it. If you can guarantee this, if you can guarantee this equality at x for this particular delta, that means you tried, you're not necessarily your best, but yeah, even your best. You tried your best to break the system at the current input. Can you guarantee that the best that I could do at this point is good enough? Because sorry, is not good enough. That means it's still, even though I tried pushing it across the decision boundary, it didn't get across the decision boundary. So yes, you might say, oh, but this you're supposed to be looking at every point in this LP ball. You're only looking at 1 point in it, and how can you make? There's no theoretical. This is why we'll see later. I mean, the good thing is that you could solve this in a an efficient manner. You can actually do this during training and defenses, but it loses this guarantees that we had in certified robustness. And many papers have come trying to solve this particular problem. How do you find this delta hat, which is this approximation to delta star in a reasonable amount of time? And these are the acronyms for all the different types of methods out there. So all these are defenses that make use of the solution. The defenses now that I'll introduce will make use of this delta hat. So let's say you have a approximate solver to this optimization. Like Pgd, for example, could be an approximate solver. How do we incorporate that in training of the neural network? Can somebody conjure up an easy way of including this? So let's say you coded up this optimization for a particular point x. It gives you this delta hat. It's efficient. It just needs a few steps of first order method, let's say Pgd, and it gives you delta hat. How can I make use of that module in training a deep neural network to make it robust? Usually what you do in training of a deep neural network is you want to minimize the expected loss across your whole training set, right? Minimize the summation loss over all these training samples that you have, meaning that I want to minimize the prediction gap between the prediction of the neural network and the ground truth. And you will update the parameters of the neural network to minimize this gap. But that's on the clean images X, your XIs, right? Your training samples. How do you think we can incorporate this into the training scheme so that we make the neural network more robust? That's exactly it. That's exactly it. So that's exactly it. So you want to, in essence, I want to now F is not known, right? Now in training, F is not, you want to learn it, right? It has parameters theta. I want to minimize theta. Usually it's minimized theta, so the expectation. So what is the best theta that minimizes the expected just loss on the training set? Now I want to minimize the expected worst case loss for the perturbations at every sample, right? So basically, you've seen this before. This is exactly what we had before, but now we want to minimize it over the whole training set where F is not known. It is parameterized by these vector theta. Okay, so that's basically the setup. This is now a min-max problem, as you see, but obviously this is super complicated to do. So what do we do empirically, so that, of course, we cannot give any guarantees. Otherwise, we'll have to solve this exactly. So what people do, what we usually do, is that, okay, let's say I'm currently at what method do you usually use for optimizing a neural network? Let's say stochastic gradient descent, let's say, right? Where at every iteration, you take the gradient of whatever objective you have and you step along it to update the weights of the neural network, okay? At the point X. So what you do instead is you want to say, I want to do the same thing, but at X plus delta hat. Delta hat is the approximate solution to this. So what does this all mean? That means during training, you're saying, look, neural network, let's say you can talk to a neural network. Look, neural network, okay? If you stay up enough and you don't sleep enough, you actually end up talking to a neural network. The problem is if it talks back, that's the problem. Let's say you're talking to it, right? So, and you're telling it, look, in your optimization, when you're training yourself, I don't want to only be accurate at the clean samples X, but I also want to be accurate. That means I want the prediction of X plus F of X plus delta, that means on the perturbed version, to be as close as possible to the ground truth also. So you're forcing it to say that even if you shift a bit, you're going to classify correctly, even on the shifted version. But keep in mind that this shifted version is not some random, you don't add some random noise. It's a function of X itself because you're solving this optimization. So ideally, it would be the worst case adversary. But since we cannot optimize for it, it'll be a good guess towards that. So you would have to create at least one adversary per, there's an expectation, right? Expectation is going to be approximated by summation over your training set size. So let's say your training set size is ImageNet. We're talking about 1 million images, which is by now a very small data set. You'll have to create a delta hat for 1 million images. So this is why finding something that is the exact maximum here is not feasible. It's not tenable, to be honest, because you have to do it 1 million times. 1 million times what? This is in one epoch, right? Because keep in mind this optimization for that we're doing here. This is for the particular F, because to find delta hat, you need to take a first order a derivative, like a gradient of F. But we're optimizing F, right? That means that from epoch to epoch, it's changing. So in one epoch, you do, let's say, 1 million of these, you produce 1 million delta hats. In the next epoch, you know how neural networks are broken down into iterations and epochs. That means you go through the whole, because this is not going to be, we're not going to be able to minimize the whole summation at once. We're going to do it in batches. So that's why it's stochastic in nature. So once you finish a whole pass through the whole data set, you're going to have to do it again and again and again. And usually we don't just converge after a few epochs. It's many epochs. So you're going to have to do 1 million generations of delta hat per epoch. And there's, let's say, 100 epochs. You're going to have to create these adversaries a lot, right? Now, of course, you can say that, maybe I'll just do, to simplify things, delta hat could be maybe delta hat could be maybe just one iteration of PGD. And there are methods, that's exactly it, one iteration. You do one step to solve this. Why? Because I'm going to need to do maybe I might not be able to do this whole solve like 100 million versions of these optimizations, right? So one iteration is fine. That means overall I'm going to be doing 100 million PGD iterations, which is way better than 10 times that or 50 times that. So there are single step PGD attacks actually that could be used. Yes, sir. Outside. Yeah. The outside one. Yeah. We do SGD. This the outside problem will be SGD. Huh? On the theta. On the theta. We'll do SGD on the theta. Yeah. So I mean, once you find the delta hat, so we solve it in kind of an alternating optimization way. So once you solve the delta hat for this, now you forget this optimization altogether, this inside one, and you treat it like any other regular training of a deep network, but for these perturbed versions. That's how you do it. Well, I mean, I'm sure that there are papers where they try. Yeah, I'm sure there's ways to, or there are papers that try to look at it in a different way, but this is the most efficient way, it seems, at least. Yeah, so but this is per image. There's one PG, so there's let's say 1 million of these. So you'll have 1 million one-step PGDs happening in parallel. You see, so let's say your batch, let's say I want to minimize over this particular summation over a batch. In the batch, there's 100 images. I'm going to have to do 100 of these optimizations. Okay? Each one I'm going to approximate with one PGD iteration. But these are different optimizations because these are different X's. So I think this is a bit, so this is expectation over X. Maybe we should have just put this as a X over here. So this is will be approximated as a summation over I. And this will be f of xi plus delta I theta comma yi. So it'll have to be for all these sepals. This is why SGD is used. So stochastic gradient. So you sample the batches. Yeah, the images themselves. Which ones you will include in the batch? Yes, that's done. Yeah. Sorry, I flipped through it. Okay. So as you see, so while we started with a kind of even though the threat model is simple because it's additive, even though the semantic constraints are simple because it's an LP ball, even though it's we talked about maybe methods to try to solve this in a worst case way, in a global optimal way, but you see that in the end of the day, we want to build a defense against these attacks. We want to make it robust. That was the purpose of my motivation at the very beginning. How do we build networks that are robust to even to these attacks? Well, you see that it quickly becomes expensive and hard to do, right? So anybody who can come up with ways of making this more efficient, have more theoretical guarantees, have more people, of course, are working on this, but this is a very interesting. Still, there's still lots of room for improvement, lots of things to be done, even on this simplistic version of robustness, of robust training. So now imagine like this threat model X plus delta becomes more complicated. Like imagine that this constraint becomes more complicated. Imagine that, anyway, you can imagine a lot of things. It just gets more and more complicated from here, and it's already complicated. So, but at least now you have kind of a mathematical formulation of what it means to train a deep network in a robust way. It's called adversarial training because you're creating adversaries in the training mechanism. But there's no certification guarantees. That means you cannot guarantee that once this training schedule is over, that once it's finished, that give me a point X. I cannot guarantee that every single point in delta will not fool the network. There could be examples within the constraint space that fool it. All right, so pros and cons of empirical robustness, which is what we talked about, trying to solve that optimization in an approximate way so that it's tenable to a reasonable training time. And then the certified version, which Motasem will talk about right after me, on like how do you provide guarantees that there does not exist an adversary within whatever LP ball or region, certification region that you provided. The con is does not scale to large models. We talked about that, but it does give guarantees. And empirical robustness the other way around. Okay. Now, the question was like I go back to the cyclic one. This is the paper, right? If you want to look it up, it's quite interesting. Quite interesting. So this is the paper that that was published, and it just exemplifies the cyclic nature of okay, a new attack comes out. A defense comes out after that, and then it keeps on going back and forth. And there's a benchmark, by the way, online benchmark with the leaderboard. There's all the main attacks that are available in the world. The main ones are there, and whoever wants to upload a defense can upload it and see how well you do on the attack, and you get on the leaderboard, right? It's called the robust bench. Look it up. It's there. It's nicely done. They keep up to date with the various attacks, and these are empirical attacks, right? So you just you upload your defense model on particular benchmark data sets, let's say SciFar and other MNIST and other data sets, and it will rank you on how you do. Can you defend against these attacks or not? So this paper came out, and in the abstract, it says that in a case study examining non-certified white box secure defenses, forget what white box means, forget that. It basically means you are given access. We're not, I mean, there's many details that, of course, we're putting under the rug and different types of defenses and so forth. White box means I have access to the parameters of the network. Okay, I can do a gradient with respect to the parameters of the network. That means everything is fully exposed to me. It's white. Black box attacks, for example, it's a black box. I don't know anything, neither the architecture nor I just know that here's the input, gives me the output. I don't know what's inside. White box is I know everything inside. And then, of course, there's the gray box, which is I know the architecture, don't know all the weights. I can take a gradient maybe, and it's like in between, middle ground. But forget what that means. It just says that in a case study examining non-certified, empirical defenses, non-certified at ICLU 2018, we find obfuscated gradients, their attack, are a common occurrence with 7 of 9 defenses relying on obfuscated gradients. So this paper says that we're gonna attack these defenses because they have this property called obfuscated gradients, and 7 of the 9 use this. And so our attack breaks, successfully circumvents 6 of them and 1 partially. And so basically in that conference, there was 9 defenses, 7 of them had an issue, right, that they found, and then they broke them all with 1 attack that they had. And the interval of time between that paper and those papers we're talking about 3 months. So there's a cyclic version. So now, okay, so now there's an attack, right? This becomes a part of that benchmark of the leaderboard and all that for all possible attacks. Then the next generation paper would come up with a defense against obfuscated gradients attacks, and there are other defenses. So obviously, if you certified that no matter what additive adversary there is in this LP ball, you will not be able to fool the network, then you wouldn't have this back and forth cyclic business, right? That's it. I mean, you guarantee there does not exist an adversary. So you cannot do this, like come up with an attack, call it Bernard attack, and it will break your defense because it's certified, right? It's certified, it's guaranteed. Now, because of the empirical, because the defenses that are mentioned here are empirical defenses, no, right? That's not the case. You could break them with adversaries even inside the ball. What Motasem is going to talk about next are certifiable or methods to certify robustness against particular threat models, let's say additive attacks, where there does not exist an adversary in this. You can guarantee in the way that you train the method, in the way that you come up with the neural network, you can guarantee that there does not exist an adversary in that LP ball, okay? And therefore, that's it, it stops there, right? Now, the question is, and he will describe it better than me, is that this region in which there does not exist an adversary to break the network, you kind of measure how big it is, okay? So because you want it to be as big as possible around the point. So this is why he's going to talk about certified regions. How big is a certified region? And of course, the bigger, the better, right? So the bigger the region is, that means the more guarantee you have that a bigger portion of the input space is covered and certifiable. There's certifiable guarantees against adversaries in that region. So that's how certified robustness methods are compared. So the method 1 comes up. Yes, it guarantees that there's no adversaries, but the biggest region that it could certify is this big. Then method 2 comes up and expands it. Expands it. This is how competition in that realm happens. Basically come up with methods where you can certify and guarantee bigger and bigger regions in the input space. Okay, and Motasem will be talking about that, I think, next, right? So before Motasem comes up, any questions, because he's going to be taking over and I'll be seeing you later. Any questions before we flip the thing? Yes.
Is there any oh, thank you. Okay. Is there any research involving something like that on federated learning? Because we were watching Peter Richtarek's
That's a great question.
And
Motasem has a, no, we can't say we're being recorded, so this is going to be like in double blind. Anyway, there is a work under construction that may or may not be reviewed, submitted very soon as tonight, on that exact same thing. So certification in FL scenarios. And Motasem actually has been working on that. Because that's a great thing, right? So because federated learning presents a great environment for attacks, right? That's the thing. Because you want to create federations, you have less control. And so maybe it's easier to attack the method. And so how do you certify against these things? So yes, I mean, there's...
Yeah, my reasoning on that was that your bottleneck is mainly on communication, right? So you had workers with some certain portions and batches of data, so they could do the Pgd steps, for example.
Yeah, true. There's work. Yeah, there's work being done. Yeah, exactly on that. Yes. Right. I'm glad we're converging to ideas and that are either ongoing or even futuristic. That's really good.
So the last remark that you said, that we were expanding the spaces that we wanted, like the big circle, the bigger circles, the bigger the circle.
And certification, yeah, we'll talk about that.
And like, what if you train a model in a way that you have much more bigger circles? So I see it in space, like you have for every picture, you have much more bigger spaces. When you introduce another time, like a new picture to the model and you want to train it, you kind of don't have enough left space in the whole space of optimization in itself. So you don't have like...
Can you rephrase the...
Yeah. So for example, for every picture you have this kind of space. And what we're trying to do is that we're trying to expand the region of that space.
Yes.
Exactly. Okay, so when we introduce a new image to the model,
yeah,
and we want to train over it,
yeah,
we're gonna try to find it in the space and make a new circle, for example.
Yeah.
And aren't we afraid that the more certified our method is, the bigger are the circles, so you don't have enough space for a new point?
Decision boundary to different points.
Yeah, so Motasem has some nice figures on that. So the main idea of certification, especially this particular method called randomized smoothing, is if you train a network in a nominal way, in a regular way, the decision boundary goes back to decision boundary. It's very jagged. This is why you can go from one point and very simply, with small LP norm, like move it from one part of the decision boundary to the other. The idea of randomized smoothing, which is a very well-known certification method, is to smooth out the decision boundary through a process that Motasem will talk about. So that way, if you smooth it out, then there's less of these jagged points that you can easily perturb. That will increase it. And by the way, when and Motasem will talk about that. We're talking about circles, symmetric in all directions in this high-dimensional space. Why should it be that shape? Why can't I certify ellipses? Motasem will talk about that. What about if I want to certify other shapes, right? Because a circle is great, but I want to, in theory, certify as big volume as possible in the input space. It doesn't have to be modeled as a symmetric, isotropic space, right? And so Motasem will talk about that too. There's been innovations on that front.
About this Pgd, it will be in most cases only one iteration is sufficient.
Sufficient for what?
I don't know. In one iteration, the gradient direction is the greatest axiom direction. If you just take one step, it would be. I mean,
it's not sufficient. No, it wouldn't be sufficient. I mean, but it's the most efficient.
Is the most efficient
yeah,
step.
Yeah, that's for sure.
So preserving the semantics. What do you think? Can you quantify that one somehow? So just by eyeball norm, what do you think?
It's a modeling task. So
When you say preserve the semantic, when you see you don't see the difference, how can you quantify that mathematically? Is there any
people in computer vision have been thinking about that for a long, long time, and all of these things are models that are not perfect, but it's something that you could write down mathematically. Because at the end of the day, you want to use it in an optimization, right? So you need to analytically define it. The best way to see if something is semantic is that you have a human in the loop, right? So I look at it, Raul looks at it, and that's fine. But I can't put that inside an optimizer that I want to take gradients over that, right? So that's the unfortunate thing. So there are constraint spaces that are much more complicated, and therefore make the optimization much more complicated. Yes. So, for example, if the threat model is not additive, it's like spatial transformations. Motasem will talk about that. You can generalize the family of these spatial transformations, these deformations, parametric deformations. Then you can create a threat model of that type, where the threat model is it's not the simple x plus delta. It's a more complicated function of x, but it's parameterized by the deformation parameters. And the deformation parameters have an LP ball, constraint on them. That means you cannot deform too much. Motasem will talk about that in the context of certification. How do you certify against rotations? How do you certify against translations? Not only additive noise, right? Additive perturbations. So he'll talk about that. But yeah, so the more semantic you put the constraints, the more complicated the setting becomes. And as I described here, if you want to put this inside a defense, then and you might need to do it millions of times. You need to make it efficient enough for it to be realistic, right? So you have these two competing things against you, right? So one, you want to make it more certifiable. The more robust is the better. That includes more computation. And on the other hand, you need to come up with a defense that's efficient, that actually you can deploy. So these are competing. Yes. I've seen papers on neural networks called LSTMs, these long short-term memory networks, and on transformers. They do time series. They're meant to process time series, so you can attack them in a similar way. So over here, I didn't specify F to be any kind of. It was a black box, right? It could have, the input could have been an image or a video or a time series of tabular data. It didn't really matter. The only difference here is just one thing. If it's if the input is of a discrete type, for example, language, okay? So let's say my neural network takes as input a tweet. That means, let's say, a sentence, and outputs whether this is a positive sentence, a neutral sentence, or a negative sentence, right? And I want to think about what are adversaries that will change a positive tweet into a negative tweet or a neutral tweet, right? It's an attack. Here, it's a little bit complicated than what I described, because, okay, you do gradient descent, and to what though? To delta, which is additive. How do you add letters together? It won't be on letters. It'll be on representations of the sentence. So you'll be adding delta perturbation onto the representation of the sentence. But that addition, that perturbation, might not actually, you have to map it back to natural language. So it might not actually make any sense. And so in that case, it gets more complicated than what I mentioned. But if you think about it that way, you can actually attack language, if not only images. So what word do you add, delete, whatever, change, so that you go from neutral to negative or positive. In that case, it's a little bit more complicated, because your input space is not really the raw language, it's the representation space of language. You don't go to the character level, but a representation of all the characters together, right? So that becomes more complicated. That's an interesting, that's just an interesting thing to explore, to be honest. I don't know much. I know that some people are trying to do that. They're trying to build language attacks. So that because it's much easier to implant a word here or there than it is to maybe rotate an image or something. You can conceal it very well in language, but it has to make sense, right? So the tweet that you create has to be an your perturbed tweet has to still be a legitimate English or language, right? So that it has, doesn't break any grammar rules or semantic rules, Right. Yeah. Yeah, they can change the words, the order of the words, deletions, insertions. But it's an interesting thing. So although I give the examples that I gave you and I abstracted it to input X, but X could be language. X could be time series of whatever, characters, words, frames in a video. They could be whatever. So this kind of setup is pretty generic. Now for specific input domains, extra specification has to be added depending on the domain. Yes, but it's interesting. Imagine you can adversarially attack an NLP model out there. So, and then how do you make that thing robust? And it's an interesting thing. There was a question up there. Yes. I said what? Say it again. Sorry. GAN is a general way to. Did I say that? GANs are, for me, GANs mean these generative adversarial networks. These have specific forms and purposes and objectives. I know of some papers that use it to generate the attacks instead of solving an optimization. But anyway, your question. Sorry, I don't think I said. Can you use a GAN for defense? Actually, some people have. Yes, you can, because the idea is that if I know that the image or the input that's been given to me is perturbed, can I train a GAN to unperturb it? There's GANs that have been trained to do deblurring, denoising, right? So if you give me an image that's blurry or it has holes in it, if you wanted to fill it in, or it has some Gaussian noise in it, I want to deblur it, denoise it, remove this perturbation. GANs are a nice way of, or a typical way of doing that. So if you think of perturbations as this particular type of noise, then you could maybe train GANs as a way to remove the noise and then, do a forward pass through it. Yes. You could do that, yes. And I think I've seen papers that have tried to do that, yes.
So my second question is, so because we could do that, I'm wondering, because you have way to compare different methods. Yeah. And do you have any idea about how GAM score compared to the other method?
Not off the top of my head, no. For defenses, you mean? Empirical defenses?
Yeah, like you saw an abstract.
There's a benchmark, the robust bench leaderboard that maybe one can visit and see if these GAN methods are even up there and how they compete with other methods. But off the top of my head, I'm not aware. Yes.
But typically, the noise that is it like high frequency noise or low frequency?
This is great. I mean, you guys are coming out. Yeah, this was a paper from Google, I think, about exactly that. So they saw that it was in the high frequencies, right, guys? Mostly spatial frequency of images. Yes. So the Fourier transform of the image in the image space, the input space. So it turns out because if you use additive threat model, right? Yeah, there was an interesting paper on that. And actually, Hassan, where's Hassan? I don't know if he stepped out. Hassan is actually, he will talk to you about a paper or a work that he's been doing on backdoor attacks. That means how can you implant these attacks inside the training images? And he does that in the frequency domain using this idea that the high frequencies in images are the ones that are more volatile to perturbations. So he'll show you heat maps of, you know, which frequencies are the ones that if you perturb more, you get more changes in the output of the network, and those are high frequencies. That's a great observation. Yes. But these are frequencies of the images. These are not frequent. So in this case, when you talk about SGD, these are what frequencies? Frequencies in the parameter space, maybe. Here we're talking about frequencies of X, No, but this is in the parameter space. Yeah.
Basically, the parameter space, the feature of semantic value you get is really low frequency in that definition. I'm just wondering about the question is that number of costs of getting many and many.
Yeah.
Okay, then I suppose you need some high frequency. The difference is that if your, let's say your accuracy, the test accuracy of your operators, one is for 10, the other is for 1,000. Let's say the whole goes like near 100%. I suppose the more classes you get more difficult time, because the more accuracy maybe mathematically you have very low accuracy when you do the classification. The bar is very low in terms of.
When you have higher number of classes, you're saying?
Even the higher number of classes that you need a more accurate model, right?
Yeah.
I guess maybe more difficult to attack.
So there's Hassan will talk more about this. I don't know if he has an ablation study on the number of classes. That's a good point. The frequency bias is in, so just so that everybody is on the same page. So this is in the parameter space, right? It's not how you train the. We're talking about. I think the question was about additive on the input space, X, right? So it would be interesting to consider both, right? So but just one thing, because they show that these high frequencies are quite open to being attacked. But a simple defense against them, it turns out that Jpeg compression. So what does Jpeg compression do? It's exactly that. I mean, it just does DCT transforms and it removes what? The high frequencies, because there's not that much energy in these Fourier frequencies of images. And so it turns out that, I mean, okay, you could devise attacks, you know, to embed into these training samples, but at the end of the day, instead of using a GAN to unperturb or whatever, simply just, you know, remove those frequencies. You know, if I know that that's where the perturbations are, what Jpeg compression will do is just remove them, and so then you make it fine. And you know, I mean, with Jpeg, you lose a bit, but you don't lose a lot of the quality. So, but of course, there's more complicated attacks, and Hassan will talk about his, and there's defenses against it, and so it's an interesting setup. But that's a great observation, and more people are looking into why it's occurring. What and which layers of the network are different frequencies being learned, really? And how do you kind of train the network so that it's so this frequency perturbation or this bias in the frequency domain is more distributed and not just in these particular places? It's a very exciting area, to be honest. Yes, Rahul. Yeah.
You still do the gradient type of method for the
input.
For the data.
For the input, yes. Yeah, this is what I was trying to say. Yes, there is a frequency bias. Same between what and what?
Same as the parameters.
I don't know. I mean, I guess we need to. I don't know much about this frequency bias in the parameter space, to be honest, to make a comment. But I do know that there does exist a high frequency bias in for robustness sake in images. Not necessarily, because we don't put any constraints on what delta should be in the frequency domain. That delta that solves the optimization could be anything. And in many cases, it looks like Gaussian random noise to us, which is high frequency, actually.
No, that is not necessarily. This I'm just confused.
Yeah.
That would be a low frequency in that definition.
Yeah, and it could be high frequency. There's nothing that kind of encourages it to be high frequency or low frequency when you solve that optimization. We're talking about the perturbation itself. So this is why it's interesting to understand why there's such a bias, frequency bias. I mean, it could be because of the same reason, right? I don't know. I don't know enough about this frequency bias in the SGD sense. Yeah, that would be very interesting. Maybe it's the same reasoning, to be honest. Yeah, and maybe it's a byproduct of how these perturbations are being created. Maybe Pgd, it's a byproduct of Pgd or something. Maybe. Yes, sir.
So, in your opinion, or maybe this frequency bias.
You mean frequency bias in the parameter space? That I don't know. I cannot comment on that. Yes. That is correct. Additive. Yes. Motasem will have some nice figures on that. Yes.
So, it could be related.
Yeah, for sure.
So it could be like each thanks to the fact that the capital of parameterization, but at this sort of randomness in the parameterization, you smooth it out and then.
I don't think it's over parameterization because when Motasem talks about randomized smoothing, the number of parameters is the same, right? So it's it could be large. For us, over parameterization means that the number of parameters is large, right? So we make sure that it doesn't overfit. So if what you're, we make sure that it doesn't overfit by looking at how this model behaves and generalizes on the validation set. So that's not it. But the jaggedness is because of the way that it was trained, I believe. In my opinion, it's because of that. So this SGD that is agnostic to the idea of adversaries, of robustness, is just, I want to be good at this point. That's it, right? I want to be very good at these points. And so you end up getting these jaggedness. So you don't sacrifice the loss at points to make it more robust. You don't have anything that you're trying to achieve on the robustness side, right? It's just about, in a nominal training, you just care about getting the loss at these points, not on the continuous domain, on these particular points to be good. That's it. So what robustness does is saying, no, you need to be good not only at these particular samples in this input space, but in also regions around them also. So it's a kind of, think of it as, yeah, it's like more of a, yeah, so instead of having this point-wise, losses, you have losses on bigger parts of the input space. This is how I would describe it. But yeah, so no problem. Any other questions?
Bernard, maybe we'll move on now because we've got another 90-minute session. Thank you very much.
Thank you, guys. Thank you, everybody.
Session. Thank you. Let's break for 5 minutes, maybe give everyone a chance to kind of relax a little bit. Yeah.
Great. Huh? Who's gonna work on the reps? We should capitalize on our time.
But not great.
Yes, thank you.
Take off the mic before you leave.
Oh, definitely. We don't want to talk anything
Because the
sensitive.
poor
Huh?
guy needs to.
That's great. Definitely.
Remember to put these on you.
Yeah.
Okay?
And it's hot mic.
Thank you.
If you can bring another window.
But what's the current
Yeah, so, but I would prefer them not. If you can bring them, that would be.
Yeah, I understand, but there's so many people to go to
Middle like this.
Yeah. Okay.
Yeah.
It's a constant factor. I don't know. I don't know today. I know that it's the space variable, the data becomes because you just want to go.
I would like to introduce myself. I'm Aku. I was supposed to be in the CRD project. Some machine learning. So the was talking about this by meaningless name, and they have a definition of the spectral bias. How they do a network, so the lower frequencies. So I think the idea is that if we have a trigonometric calculation, and the high frequencies of the data. Those are the whole frequency domain data, the weights, frequency. Then you can so you have no. Then those are the same.
Right.
I would say we can think about this.
I thought you were looking for
Yes.
but that's like
We have a picture of one layer where that's what we do the metric calculation. How do something of distribution? Only given data.
I don't think so. Okay. No, and that's also the for that particular
then the weights, first weights, and we call them times and then the optimal distribution minimize constantly or the function, the underlying function. Then you will have your tonic function high figures. Then you need to sample.
Yeah, exactly.
We have that for but we need to but it's very special. But you use parts of it. We're very good. Yeah.
What I'm saying is that this is not like people who
actually works, but really like the same way than I find. You don't have the same feeling with a lot of stuff.
And the good that showed this bias and showed so basically they took frequency here, right? So nobody told me this because that's why
Wait, let me just try to put this thing. Right. I don't know if this works. Does it work? Yeah, it works, right? Works.
If we could start getting ready to resume, we'll try to resume in 2-3 minutes, please. Okay, so I'm going to resume now in the interest of time. So we still have 90 minutes left, roughly. So we'll finish at 12 instead of 11:30. So the second speaker for this course is Motasem Alfarra, who's a PhD student in ECE, part of Bernard's group, and he's going to add his commentary on certification. Please go ahead. Thank you.
All right. So does this work? Everyone hears me? All good? Can you? Yeah. Okay. Fine. So by this time of the talk or of this mini course, almost everyone should be familiar with what do we mean by an adversary and what do we mean by robustness. And whenever someone comes and tells you, please build me a robust model, the first question should be, you want this model to be robust against what? And so far, due to the simple mathematical formulation, we adapted this additive model, right? Simple, just additive pixel intensity perturbations, right? And by the end of Bernard's talk, you saw that empirical robustness is nice, but maybe it's not the best direction because it's like a cat and mouse game, right? Someone develops a defense, then next conference or like maybe next month, someone else develops an attack, and then this attack works a defense and so on. So we need to put an end to this game. And one way to end this game, I mean, it's not an end, but you can think about it, is to provide this theoretical guarantees through certification, right? So I'll just do a quick recap and definition just for one slide, just to just be on the same page with everyone. So what do we mean by certification? So we mean by certification is that if we have a classifier F and we have an interest region of perturbations like this capital delta, we want our classifier to have a consistent or fixed prediction for all points in this region, right? And this is like just the formulation that was presented earlier, where I just want the argmax not to change. I don't care about the probabilities anymore. I just care that the maximum class in terms of probability will not change as long as this perturbation inside this delta. And someone might come and ask, how can I define this perturbation of delta? This is actually like an application specific. So for example, if you're targeting building a model in a specific application where you know, like for example, your sensors might experience some noise within this region, then this is the region that you target to certify when building your model, okay? And we say like back then is that one way of solving this is to solve for the worst adversary in this region. So you want to solve for this delta star that maximizes some loss function where your perturbation should lie in this delta perturbation. And we said the problem here. And back then, Bernard talked about the scalability and why solving this problem is expensive. I'm just going to walk you through a very simple method that shows how this problem is not scalable for deep models, okay? So imagine that we have a very simple architecture, just that classifies digits. For example, this is a 9, or I don't know, like looks like a 9. And your model is just concatenation of several layers. Say the first layer is just convolution, second layer is just this rectified linear unit, then another convolution, then maybe a fully connected or like a linear layer. And this is just a simple 4-layer network, okay? So what's going on is that suppose like we're still working with LP balls, and this is what we call adversarial polytope. So we have an infinity ball around the given input point that we really want to find delta in which this, in this region that maximizes some loss function, right? That we had earlier. One way of doing an easier approximation of this problem is to propagate this region, right? So you have, instead of forward passing a point, you propagate this region, and you know how would this region look like after a linear projection. So you pass this region through a linear layer. You know how does it look like I don't know, as a squished polytope. Then after the linear, after this rectified nonlinearity, it's going to look like something else, and so on. And you can see that after just few layers, even with few simple layers, you might end up in a very, very complicated region, right? Which is just over here. I know if this works. Yeah, which is over here. And then you know how to maximize over like an infinity ball. So you always approximate this polytope with an infinity ball, and you might end up with a very loose over approximation that will not become very useful. And you still want to solve for the worst case perturbation, right? And this shows that even in this setup where you have like very few layers, this might not be very practical. And I'm just quoting the same statement that was shown before. If you have 50 layers, like resident 50 or 50 just defines the number of layers, then you can see how overcomplicated the shape that you started with a very simple just LP ball could become. And then probably working on an over approximation there is going to be like very loose and not that meaningful, right? So we end up in saying that methods that provide these certificates, they're nice, they provide guarantees. You cannot fool my model in this region, but they do not scale. But actually, like this is not very, very, very true, because we're going to show one method that scales. I mean, this is not the only method. It is one very interesting and very recent method, and we're going to talk a little bit in depth about it, which is called randomized smoothing. Okay. Up until this point, does anyone have any question about certification in general? Is the problem clear to everyone? All good? All happy? Okay. So let's start with randomized smoothing. So what does randomized smoothing do? Is that we want to address this scalability issue or scalability challenge in certified robustness, right? So let's consider any classifier. I don't know why there's like a white rectangle, but yeah. In any case, let's consider this any classifier that maps from Rn to some probability simplex. What randomized smoothing does, in a nutshell, is that it constructs a new classifier called G, where G, instead of pushing just one input x through f, it outputs a regional prediction or a prediction over a region of inputs around x. So this method says that instead of having just one model f, and whenever you want to query a point, whenever you have an input x, you push it through f. No, I'll take this f, put it inside the wrapper, inside this expectation. I'll do many, many forward passes in the case that I want to estimate this expectation with Monte Carlo samples, and I'll estimate this expectation. And someone might want to say is that this is a little bit not clear because we don't know how to choose this distribution, right? And why on earth would anyone increase the inference time cost? Because in the past you had one f, right? So you want to query a point, someone gives you an image, tells you how can I classify this image? You push it through f, then you get the logic. Now it's no longer the case. Someone gives you a point x, then you sample many epsilons from this distribution D, you push all of these x plus epsilons, aggregate these predictions, and this is going to be your prediction, right? So just graphically speaking, suppose we're back again with a very simple binary classification problem. We have two classes, and we have just one input x, right? In the past, we were just saying that f will say that x belongs to class 1 because it falls in that class. But now, in the case, let's say that the distribution that we're sampling from is just simple Gaussian, isotropic Gaussian, right? With sigma square variance. What's going to happen is that you're going to sample lots of points around this x. You'll forward pass all of them and compute the expectation, which is like an average across all of these, right? And one might ask, like, how is that beneficial? That's beneficial because even if you fall in this very nonlinear, highly nonlinear regions, like very kinky regions that belongs to x2, and you know that Maybe this is just due to over-parameterization. Maybe this is due to high dimensionality of the input space and so on. Even if you fall there and you sample large enough number of input data from this distribution, your majority vote still belongs to class 1, right? So this is equivalent to smooth the decision boundaries such that highly nonlinear regions will become less nonlinear, okay? So it smooths any arbitrary classifier, right? Is this clear so far? Just the method just takes any classifier. Instead of doing one forward pass, I'll do many forward passes, and I'll aggregate these predictions. Cool? What is special about this? I mean, we just maybe multiplied the inference cost instead of doing one forward pass to an expected number of forward passes, like 100 or 1,000. So why would anyone do that? We want to do that because of the following characteristics, that you have your classifier G, and suppose X is correctly predicted. So if you have an X, Y input label pair, you forward pass X through your classifier G. We're no longer talking about F, right? We just put F inside this wrapper. Then if you check the argmax of G, then it is Y. So you're fine. An image of a panda, your smooth classifier tells you this is a panda. What this smooth classifier has, that it tells you that this G is robust, i.e., the argmax of all perturbed versions of your image, which is the argmax over X plus delta, is going to still be Y for all delta satisfying this inequality, right? And what does this inequality say? It just says that an L2 norm of delta is less than or equal to some value. And let's not care about the value. Let's just look at this in a bigger picture. This says that one could draw a circle, right? Because this is an L2 norm around X, with the radius quantified by this amount, whatever that amount is just an overcomplicated expression, where adversaries cannot exist. So even if someone tries to construct a new attack today, as long as the perturbation is satisfying this inequality, you have no choice of flipping the prediction of your input, okay? And let's take a closer look on what does this expression mean. I mean, the first term is just sigma over 2, where sigma is just the standard deviation of your Gaussian distribution. Then you have this phi inverse, which is just an inverse CDF of your Gaussian distribution. And PA and PB are the top 2 probabilities of your smooth classifier. So suppose you have an image of a panda, you push it through your smooth classifier, it tells you this is an image of a panda with probability 0.8, right? Or 80%. And this is an image of not panda with probability 20%. Then PA is going to be 0.8 and PB is going to be 0.2, okay? So it seems like a neat expression. And now we can certify models, regardless of these models, with this expression, right? We call this expression, which is this the product between sigma over 2 and this difference between 2 inverse CDFs, as a certification radius. And the nice thing about this expression is that this holds for any classifier, right? So we didn't make any assumptions on F. The only assumption that we made on F is that it outputs in some probability simplex. I mean, like ideally, this also holds for any classifier with bounded output space. Doesn't necessarily be a probability simplex, but with probability simplex, the derivation becomes just one step easier, right? And what does this say is that we're again with our decision boundaries, but now this is the decision boundaries of G. We can draw a circle or a ball around a given X with the radius R, where this is R, where adversaries cannot be found in this region, okay? So indeed, randomized smoothing gives like, let's say, a scalable approach of certifying networks. And now we know how can you quantify this region. Perhaps someone could incorporate this radius during training to maximize it over all samples on your training set, okay? So any problems with this nice statement so far? Can anyone spot any problem? I don't see problems as bugs, but problems as vague things, like things that we didn't really incorporate. And just a small hint, there exist problems. No problems? Anyone? Okay, so the first thing is that we assume that this classifier classifies X correctly. And who says that that is the case? So what happens if the classifier, if your smooth classifier is actually outputting some erroneous prediction from the get-go? What's going to happen? It's still going to certify this point, but with the wrong prediction. So it's your responsibility to train your smooth classifier such that it outputs correct predictions for given inputs, okay? The second thing is that I gave you like one distribution, which is Gaussian, but this Gaussian distribution, although it's isotropic, still parameterized by the standard deviation, right? How on earth are we going to choose the standard deviation, like the parameters of this Gaussian distribution? Okay. So suppose like an oracle just told you, okay, I wanted to use this Gaussian distribution with this smoothing parameter, i.e., like, I don't know, like a sigma of your favorite number. It could be like 0.1 or 0.2, whatever. Okay. Then one way of training this classifier and incorporating this noise is basically doing Gaussian augmentations, because what's going to happen is that at inference time, you're going to push Gaussianly perturbed samples through your classifier. So you expect your classifier to perform really well under Gaussian perturbations. So perhaps it's better to train with Gaussian augmentations, right? So in training time, perhaps you do some Gaussian augmentation with the sigma that this generous guy told you to use, right? And then you train your model, okay? And also, like, although this is simple, follow-up works actually incorporated adversarial training, which was just shown by Bernard, right? This minimax game, or like some regularizers to maximize this radius. I mean, there's like a huge line of work. Like, although this paper is just 2 years old, it got almost 1,000 citations so far. And there's a huge line of work. How can you actually incorporate this in training? How can you maximize your certified region in training, and so on, right? Because the statement doesn't give any hint how you should train the classifier, but you kind of expect how do you train it, okay? The second thing about this is that how are you going to choose this sigma, right? Because in the previous slide, someone gave it to you. Now it's no longer the case. So what's going to happen is that if you have like a large sigma values, you kind of expect that the right-hand side is larger, right? Which is very desirable. Like, I want the right-hand side to be as large as possible. I want to certify larger regions, okay? However, if you choose sigma to be very large, then maybe you could sample more from the wrong prediction regions, and then you have inaccurate prediction of your smooth classifier, and thus you fall into the trap of certifying the same input, but with the wrong label, right? So how are we going to choose this value? It's kind of not very clear up until this moment. It's just a hyperparameter where actually you could show your performance under like a variety of values. And let's just look at this curve, where this curve shows like an empirical performance, or like empirical performance of a given classifier, but in a certified manner. So the x-axis of this plot says radius, which is the certified radius computed by the formula up there, right? The y-axis is called certified accuracy. And we mean by certified accuracy, I'm looking at the percentage of some held out test set that the classifier is not only classifying correctly, but if I go to each of these samples and compute the right-hand side there, which is the certified radius, I'm going to get at least a value of some x-axis values, which is the certified radius. So just as an example, let's look at this black dot, right? This says that, for example, the blue curve, which corresponds to sigma 0.25, has a 50% certified accuracy at radius 0.5, which means that 50% of your test set is not only classified correctly, but if you compute the certified radius of each sample, it's going to be at least 0.5, okay? And I mean, there's another example. For example, if you look at this point, which is a certified radius at 2, and you can see that the certified accuracy is 20%. So you have 20% of your test set is classified correctly. And also, if you compute this certified radius, it's going to be at least 2. And you can see the trade-off, right? So the trade-off says that if you have very small sigma values, like 0.25, your certified accuracy at very small radii is much higher than the other curves, which means that you could output more correctly classification points, right? So you could classify correctly more points. However, if you choose larger sigmas, like the green curve, which corresponds to sigma of 1, then probably you could certify bigger radii, such as radii of 3.5 and 3, which other sigmas cannot certify. However, that comes at the expense of worse accuracy, okay? So again, it's not like a solution, but you kind of have the spectrum, and you determine, you're the person who designs your classifier, so you know where the expected norm of perturbation is gonna happen in test time, and then probably you can choose this sigma. And this is like a well-known classical result. It's called robustness accuracy trade-off. So better robustness means smaller accuracy or worse accuracy. So any questions so far? No questions? Yes.
Your model. Sorry. So I wanted to ask you how much do you have to pay in terms of times that you have to evaluate your model in order to get this information about the robustness of your
So the point is that there are two things. If you really want to do only inference, then you only care about the argmax of your classifier, right? Your maximum probability. And for that, you don't really need very high number of samples, maybe 100, 200 should be enough. But if you want to compute this probability, which is PA, for example, to compute the certified radius, this is going to be very tricky, and you might end up sampling something like 100,000 of samples of this noise, and you push all of these samples through your classifier and so on. But the good news about this is that this is parallelizable, right? So you could, if you have large computational resources, classification of each augmented sample doesn't depend on the classification of another augmented sample. So you could push all of them in parallel, construct some table, and count how many of these perturbed samples were classified correctly. And by that, you could compute this probability. So it is still not that scalable. It is scalable. Like it is doable. People could do resonate 50 here. I mean, you could do it on one GPU at your lab, right, with a few hours of training or certification. But again, it's more expensive than just doing one for a pass.
Of course.
Yeah, but there's nothing for free, right? So yeah. Any other question?
Thank you.
Yeah. Because like I think like this method is crucial because like on top of it we could build lots of other things, right? Because you can see like this method is nice. It didn't make lots of assumptions. It is somehow practical, and it gives the guarantees that we really want, right? Okay. So that was randomized smoothing. Like this wasn't too long, and now we delve into anisotropic certification. And we mean by anisotropic certification is that in the previous paper, on the previous presentation, we're looking at this form of scenario. So we have two classes, some kinky decision boundaries, and we want to quantify an isotropic or like a ball around X that is formulated by some norm, right? Where adversaries cannot be found. So if we look at this point, for example, from some Cypher data set, you get this image. And I mean, it's challenging for a human to classify Cypher, but I tell you, this is an image of an airplane, right? And it is nice that you could build this region where you cannot find adversaries, but what about point that is just outside this region, but still it's relatively close to this input image? So how would that point look like? I mean, it's gonna look like something like this. We still recognize it as an image of a plane. I mean, if that was an image of a plane, but randomized smoothing alone is incapable of certifying that point. It could give no guarantees and whatsoever. And that's why maybe it's better to certify anisotropic regions, right? Because it could approximate better decision boundaries that are more complicated. And in that, we could have better chances in building classifiers that certify more samples that are alike with the original sample, okay? So we'll look in this work in two scenarios. I mean, generalized L2 ball certificate, like for example, an ellipse, or a generalized L1 certificate, which is just a cross polytope, okay? So you can see that in both cases, this perturbed image of a plane, which we all could recognize that it is a plane, could fall outside this isotropic region that randomized smoothing cannot certify. But if we're able to certify that green region or green bounded region, then probably we can certify these points, okay? So the question is, can we actually grant certificate to this? And how is that possible? Before we delve into that, I'll give you like one slide about one important concept, which is Lipschitz continuity, okay? How many of the audience is familiar with Lipschitz continuity or heard about this term before? No one? Okay. Familiar, yeah, familiar with Lipschitz continuity. Okay, so yeah. So we mean by Lipschitz continuity is if you have a function g, we call this function is Lipschitz. If you change, like if this condition happens, that if you change your input by some amount, like if you move from x to y, then your function will not go crazy. So it will not go unbounded. So the variation in your output of the function is bounded by some constant called L times the variation on your input, right? And we define this Lipschitz continuity in terms of dual norms, right? So like if you want to have your function to be Lipschitz against some norm, which is this norm star, right? Then you get this inequality where the norm on the input space is going to be on the dual norm, okay? And someone might want to ask is like, why are we interested in Lipschitz functions or Lipschitz continuity altogether? Is due to the following theorem. What this theorem says that if you have function that is Lipschitz, then you get this function to be certified robustness by construction, because you know that the output of the network will not go crazy. So you can quantify certified region. And let's go over this statement, an important statement, piece by piece. So what this statement says that if you have just a function that is Lipschitz continuous under some norm, okay, then your classification will not change for all perturbations satisfying this inequality. And this inequality looks pretty much like the inequality that you just saw in the randomized smoothing, except for two differences. The first difference is that I mean, I don't know if this works. Yeah, the first difference is the right-hand side, right? It just looks a little bit different. So we used to have sigma over 2, but we still have a difference between two terms. The other thing is that we didn't specify under what norm we're certifying, right? In the past, we specified that we're certifying only L2 norms. Here, we're just saying that if you're Lipschitz against some norm, then you get a certificate on the dual norm, right? So if you're Lipschitz against L2 norm, then probably you'll get a certificate and also the L2 norm, because L2 norm is also dual to L2 norm. And if you're Lipschitz against, I don't know, infinity norm, then probably you'll get a certificate in the L1 norm and so on, okay? But like the conclusion of this statement is that functions that are Lipschitz under some norm, they're certifiable under a dual norm. This is what this theorem says. But yeah, but how is that related to randomized smoothing? I mean, we're talking about some very interesting method. We're just talking about randomized smoothing, then all of a sudden we ended up talking about Lipschitz continuity, right? So to see like how that is related, let's go into the next slide. So the next slide, I mean, just copy pasting the theorem, keeping up for reference up there. And what this, and we're going to leverage it in the following manner. It turns out that randomized smoothing makes any function Lipschitz function, okay? And it makes it like, we said that there were two factors in the construction of a smooth classifier. The first thing is the smoothing distribution, right? And back in the slides, we just chose it to be some Gaussian, some isotropic Gaussian, and we derived the robustness certificate under that. But it turns out that this smoothing distribution determines the norm under which this function is going to be certified against, or the norm under which this function is going to be Lipschitz against, right? And we know if it is Gaussian, then we got an L2 norm, so probably that function will be certificate in L2 norm, right? And last but not least, the parameters of the smoothing distribution, which was sigma back then, controls or determines the value of L, which is the Lipschitz constant. And you can now clearly see some relation because we used to have sigma over 2, and now we have 1 over 2L, right? So there's some relation that we're going to see in the next slides. And this of two Gaussians, right? Okay. So we know now, like we're back again now with our motivation. We wanted to certify these regions, okay? But we know that these regions can be characterized with norms. I mean, not isotropic norms, but some Mahalanobis norms, right? And here's the recipe of certifying these regions, right? First, we want to find the norm that characterizes a region we're interested in providing a certificate against, right? In this example, it's an ellipsoid. In this example, it's just a cross polytope. Since we have this region, we need to find the distribution that gives us Lipschitz continuity in the dual norm of this region, right? So if you could characterize this in some norm, you derive the dual norm, and then find some smoothing distribution that gives you this Lipschitzness. I mean, it's still a little bit vague. We're going to to show a couple of examples of that. And the last thing is that once you chose this distribution, you know that this distribution is parameterized, for example, sigma for Gaussian. Then you just need to derive the expression of the Lipschitz constant. Once you have that, that's it. You just substitute your Lipschitz constant for that distribution in the upper formula, and you get a certificate, okay? So let's say we want to certify ellipsoid. And by cheating, we know that certifying, like we use isotropic Gaussian to certify L2 norms. And ellipsoids are nothing but L2 norms that are in some Mahalanobis distance, right? So it's just a linear layer multiplied with this L2 norm. So what about we try just a more general Gaussian distribution instead of sigma square identity and the variance? We just call a generic covariance like a positive definite matrix. If you construct the smooth classifier, it turns out that this function, which is the inverse CDF of this classifier, is 1 Lipschitz under this norm. And this norm is just basically defines this ellipsoid, right? Because, I mean, this norm is nothing but an L2 norm, but of sigma multiplied to your inputs, right? So it's like X transpose sigma inverse X under some L2 norm, okay? And since we have this Lipschitzness, then you just go and substitute this information, this theorem, right? It's just a simple exercise. Now you know, like you have this norm, which is an L2 norm of some Mahalanobis distance. You derive its dual norm, and voila, it appears to be an ellipsoid because it's again a dual norm of L2 norm is an L2 norm. And you substitute your guy, the Lipschitz constant, which is 1, into the formula. So you get 1/2, and these are the 2 phi inverses because this is the function that was Lipschitz, okay? Again, if this sigma was sigma squared identity, then you could separate this into L2 norm times sigma, 1/sigma, right here. And then you pull that sigma here, and you'll get your sigma/2 back again with your expression, which was derived in the isotropic case. So again, this norm is just nothing but a parameterized ellipsoid, where this covariance matrix determines the radius across several directions in your ellipsoid. And yeah. Next, we go into general closed polytopes. And yeah, you have a question.
I mean, my question is about, like, we've been saying that we've been doing normal noise somehow.
What? Okay, can you?
Yeah, we were doing Gaussian noise.
Yeah, we're still doing Gaussian noise, but instead of isotropic Gaussian noise, it's just a general Gaussian
definitely.
noise.
But what if you change like your data, give it a different kind of noise? Would
Yeah,
you
this
be
is-
certified in that?
So, I mean, you choose a distribution. This distribution defines the norm under which you're going to be Lipschitz, or the norm under which you're going to give a certificate, right? So if you're interested in a given distribution, you just need to see under which norm is your smooth classifier under this distribution is Lipschitz. And the dual norm of that norm is the norm under which you're going to give the certified radius.
Yes, but in general, like to train your model practically, you need to kind of certify it against a lot of like distributions, right? Not just the Gaussian one.
Again, it's an application dependent. So if you expect in inference your perturbations to be in this region that is parameterized by some ellipsoid, then probably you need to use Gaussian. If it is another region, then probably you need to use another smoothing distribution and do all the math. I mean, there's a paper that we can talk about it offline. It's called Randomized Smoothing for all shapes and sizes, where it derives like for any norm, but isotropic norm, the distribution that you need to use to smooth your classifier. It's not always the case that it's Gaussian. I'm just showing Gaussian for consistency, but the next slide is not Gaussian.
Thank you.
So this is exactly that slide, right? So it turns out that once the parameters of your smoothing distribution actually are the knobs that control this Lipschitz constant. For example, in the case of isotropic Gaussian distribution, your Lipschitz constant is going to be 1/sigma. That's it. You know, it's just if you use that, you derive the Lipschitz constant is going to be 1/sigma. So if you tune sigma, which is tuning the amount of noise you inject to your classifier, you're also tuning the certified radius in some sense, right? Is this clear? I don't know. All good?
For the case where you have the sigma covariance,
Yeah.
you have the covariance matrix, that will be what the smallest eigenvalue of sigma, or
Can you say again?
in the case where you do not have isotropic noise,
Yes.
then you have a covariance matrix sigma there. Then I guess this would be what the smallest eigenvalue of sigma, or
If you want to check an isotropic region inside your ellipse that you could certify, then probably you're going to look at the smallest singular value of your isotropic, or like I mean, if it's diagonal, it's just the smallest element. So you want to look at the biggest ball that fits inside your ellipsoid, right?
Yeah.
This is going to be your certified region in isotropic fashion. But as we saw at the beginning, maybe like modeling the noise in isotropic fashion is not optimal, and maybe we need this anisotropic certification. Instead of looking at certified radius, maybe you could look at certified volume now, right? But that still is of importance, right? Because like most of the works are done in the isotropic.
thank you.
Any other questions? Okay. So now we know how to certify ellipsoids, right? We just use general covariance matrices for the normal distribution. And next, we want to certify this generalized cross polytopes. And again, if you substitute instead of your Gaussian distribution in this formula a uniform distribution, and then then your classifier is going to be Lipschitz, where the Lipschitz constant is 1/2, like L is 1/2 under the infinity norm. And the dual norm to the infinity norm is going to be just L1 norm, right? And this is just a norm of a scaled or like a linear projection of your input. So the L1 norm of that is going to be just a general cross polytope that is characterized by this. So since you have L is 1/2, you substitute it over there. And then you have infinity norm, you substitute your dual norm, which is going to be an L1 norm. I'm not sure how this works, the laser. But yeah, it's going to be like a dual norm. The dual norm of the infinity norm is going to be like an L1 norm, which is here, right? And then you get a certificate in a general cross polytope norm. Right? So this is just a parameterized general cross polytope. Cool? So yeah, before I go into the last part, any questions? Because like the last one is just a more fun or a more practical part, because throughout this talk, we have been obsessed, or like we have been just talking about input additive perturbations. And at the beginning, Bernard showed several examples where actually adversaries could appear in a more physical or more practical scenarios in real world. And this is like the last part of the talk. But before we jump into that, like if you have any questions, maybe this is the time. All good? Okay. So let's go into the last part of this talk, which is certifying deformations. So again, we're back again at binary classification problem, 2 classes. And we had this as an image of a pig, like this classifier. And we said that certified robustness, we want to give this theoretical guarantees that you cannot fool my classifier until this perturbation satisfies some quantity, or like the norm of the perturbation is less than some quantity R, right? But the world is much more complicated than additive perturbations. Like we have to agree that additive perturbations are very nice for mathematical formulation, but the world is way more complicated than that. So we're back again with the example where a rotated revolver is recognized as a mousetrap, or like if you just shift your image, or if you deform this image in a certain manner, then your classifier is still full. And we're interested now in giving guarantees to this scenario as well. The problem is that we could still use the guarantees from the just additive pixel perturbations, because probably you can model this as an additive pixel perturbations, right? It's just this pixel, I don't know, it just was added to its inverse value to become black and so on. But you need huge norms to be certified such that you model, such that you certify some meaningful deformation like this.
I'm sorry, can I read one question from Zoom here?
Oh.
Mohammed asked, in the case of Mahalanobis distance, how do you estimate the sigma? Does every sigma give you 1 Lipschitz?
In the case of what?
The Mahalanobis distance.
So it's like sigma is just a hyperparameter, right? So we said at the beginning, like, I mean, I could just go back to the plot. This plot, yeah. So sigma was just a hyperparameter. So it depends what regions you're interested in certifying, then probably you know what sigma you should use in your training and testing time. I mean, there are works that could automatically choose the sigma per input, but they're still under development. I mean, they're still not that famous, but you could think of sigma as just a hyperparameter that you need to choose. You just need to decide what to choose for that parameter. And again, it's the same for the anisotropic case, right? So just a hyperparameter, because you might think that this ellipsoid is better than this ellipsoid at test time, and then I want to certify this ellipsoid. Right? Okay. So we're back again. Yeah, we're back again here. So our target of this part is that we want to give similar guarantees, but to scenarios that are more practical, scenarios that could mimic more the real world. I mean, I'm not saying that pixel perturbations is not that synthetic. It could happen. I mean, input noise could happen to any sensor measurement, but I mean, how likely is it to happen compared to, I don't know, a rotated camera, like I don't know if you have a fixed camera somewhere and some kid just hitting that camera, so your image is going to be translated or rotated and so on. So we want to give similar guarantees, but for this scenario, okay? So by the end of this part, I want to say something that you can't fool my classifier. so far as long as your rotation angle is less than or equal to some theta, some r. Okay, so I'm no longer interested in quantifying input perturbations, but practical parameters that control some real world applications. Okay, is the motivation clear? All good? Okay. So let's have a look at this example. So we have an image of a 5, and then one can model these deformations or these input transformations to additive perturbations, but not happening to pixel intensities, but pixel locations. So you want to add a certain value to each pixel location, and you will move that pixel somewhere. And this additive perturbation in terms of pixel location could be as nasty as just random Gaussian perturbation, right? So you sample random Gaussian perturbation, you add it to your pixel locations. So you take each pixel, you move it in a random direction in a certain manner. And again, the standard deviation could actually determine how severe your deformation is. So if the standard deviation is going to be a little bit small, then probably the image is still an image of a 5. You increase the standard deviation a little bit, then this 5 becomes more scattered and so on, right? Or this deformation could be more well behaving. There exists some function that is parameterized. It has some knobs where you control this deformation. For example, rotation. I mean, you no longer need to generate this vector field where you shift each pixel. You only need to decide on one parameter, which is rotation angle. From that parameter, you know exactly how to generate this vector field of a rotation, and then you deploy it here, and the image is rotated. Another example is just scaling, which mimics the zooming in your camera. So you just need to define a scaling ratio or a zooming ratio, and by that, you could actually generate this vector field, and then it will actually deform your input image. It could also be shearing, could be translation, it could be any combination of both. So for example, this guy is just a translation composition with scaling. So the 5 appeared a little bit smaller, but in this corner, instead of having it centered right here, and so on. And this could be like a general, for example, DCT deformation. So you sample this from some DCT or like Fourier map, and you deform your input with these guys. Okay. So note that we're no longer saying that our perturbation is imperceptible. Like I think all of us agree that each of these perturbations is perceptible, right? So you can clearly see the difference between this image and this image. And this is not similar to the example of the pig, where we had 2 almost identical images of the pigs having different predictions. However, we should all agree that all of these images are images of 5s, right? Maybe, I don't know, like this one appears a little bit like a Z or like a flip Z, but I mean, if you really need to choose a number between 0 and 9 for each of these images, probably you're going to choose 5 for all of them, right? So let's look, how can we formulate randomized smoothing in this manner? So what do we have? We have an input image X, right? And we have some deformation map. Yeah, and we have some deformation map. And because this deformation map is sampled from some random distribution, so maybe you could shift a pixel that is located at 1, 1 by a 0.5 or 0.6 because you sampled it from some random distribution. And we know that pixel location should actually be integer valued, right? Because a pixel cannot exist between pixel 1 and pixel 2. So we need some interpolation function, right? You can think of this interpolation function as just a box that makes the image nicer to your eyes, because a pixel cannot exist between 2 locations. Okay, so I have an image, some flow that represents this deformation, and an interpolation function gives you a transformed image. And in this case, it's just rotation, right? And what do we have? In the case of well-behaving transformations, we know that this vector field is coming from some function, maybe the rotation function, and this function is parameterized by some small dimensional parameters phi. So think of phi as a rotation angle. You give it to some function, it gives you this map, and then this map's deployed on this image, gives you this rotated version of the image. Okay. And in deep learning fashion, we're just to put more context to that. So we have this P representing the vector field of the pixel locations, and you're just adding some perturbations of V of P, right? So and this perturbation is coming from this phi. So V is just or nu is just a rotation function that generates for you a field where each pixel should be moved to. And it happened that this is just parameterized by some parameter phi, such as the rotation angle. And then this transformed image will feed it into a classifier F. that we really wish to certify, but no longer against input perturbations, but under perturbations to these parameters, right? Because our target was to provide a classifier that cannot be fooled as long as the rotation angle is less than or equal to some value, right? So this is like the kind of guarantees that we want. In the past, since we wanted to certify X, we're perturbing directly pixel intensities X. And here, all what you need to do is just we smooth these parameters phi. And we say by smoothing that we're again constructing the smooth classifier, which is some expectation. But now we have this interpolation function, which is a little bit annoying. But what we're smoothing is basically epsilon is added to phi, which is the parameters that controls your deformation function, okay? So instead of doing one single forward pass Fourier model, you sample several rotation angles, and then you deform your input image with all of these rotation flows. So you have several rotated copies of your input. You push all of them through your classifier F, you aggregate the prediction, and then this is the output of your smooth classifier. Is this slide clear? So are all is everyone here like aware of what we're doing in the aim or in the target of certifying deformations? So in the past, we're sampling perturbations, adding them to the input intensities and pushing these guys, right? Oh, sorry. Now we're sampling just angles, or I don't know, shifts, or like some zooming factors. And then we transform the input by these amounts, and then we push all of these and aggregate the prediction. And then since we know, based on the previous example, that we didn't make any assumptions on F, right? It just should output in some probability simplex, then this classifier is certifiable. And I mean, so the statement looks more complicated than its actual value, but let's walk through it together. So I've just got the definition back from the previous slide. So we have this smooth classifier, right? So we again have some expectation or some distribution, some classifier, some interpolation function, an image, and the way we want to deform this image. And we know that this is controlled by parameters, and we're perturbing these parameters, okay? So we should be aware of what this expression does. Then what happens that if this classifier is correctly classifying your image, which is saying that this is a CA, then this classifier will resist all perturbations happening to the parameters phi. So the argmax of this classifier over perturbed versions of phi will still be CA, will not change. So if CA was correct, then it's going to still be correct. And these are just the two previous examples that we got from two choices of smoothing distribution. So if you choose your distribution to be Gaussian, you're getting a certificate in the L2 norm. And if you choose your distribution to be uniform, you're getting the certificate in the L1 norm. So what is new in this whole business, in this new corollary, or in this new theoretical statement, is that we're no longer certifying additive perturbations to pixel intensities, but additive perturbations to parameters controlling a deformation that we're interested in. So we're back again with our rotation function and parameterized by some phi. Then it generates for you some rotation flow field by which you're going to deform your image. You feed this to your classifier, but now we're putting a smooth classifier instead of F. And now we know that this classifier is certifiably robust under perturbations happening to the parameters controlling the deformation. So the main objective that we started with, which is building a classifier, achieving the statement that you cannot fool my classifier as long as a rotation angle or like a translation amount or like a zooming in or zooming out amount is less than or equal to some value, is satisfied by this inequality, right? So our target is there. And to work you through how can we measure this in practice, okay? So we have different classifiers, right? Different models. I mean, we don't really care about the numbers exactly, but let's look at it through the following. So we have in this table numbers that represents certified accuracy, which we defined earlier. I mean, I'm gonna repeat the definition in a few. Against three important transformations. The first one is rotation, second one is scaling, third one is translation. And now you can say, for example, this number, which is 96% on this data set, you can say that my classifier is not only accurate with a probability of 96%, or the test accuracy is 96%, but also as long as you rotate your test set by an angle that is less than or equal to 30 degrees, oh, come on, yeah, less than or equal to 30 degrees, then my classification is still going to be at least 96% accurate. And this holds for scaling. but this is with 20%. So if you zoom in by 20% or zoom out by 20%, if you shift the pixels by less than 5 pixels, like you take your input image, you shift it by 5 pixels in any direction that you want, then you're still getting certified accuracy. So you cannot actually attack the model by doing simple transformations anymore. But as long as these simple transformations are actually satisfying these quantities. I mean, you could output the same numbers, but like the same certified accuracies, but for different transformations or for different rotation angles and so on. But this is just as an example. And yeah, again, we're back again with the statement that we really wanted to achieve, which is you cannot fool my model as long as the rotation angle is less than or equal to this number between parentheses. And in this example, it's just 30 degrees. Okay. And to see how does that look like if you sample inputs from this region, for example, you can deploy some shearing. Still, the model is certifiably robust against all of these deformations, which means that if you push any of these through your model, still recognize it as the original class, which is 7, right? And also this was applied to another example and so on. Is this clear? All good. Yeah, question in the back.
Can you please?
Thank you, guys. So when you are at the person training the model, do we use the data augmentation?
Yeah. So
with
that's an excellent question, because we're again with the same problem with randomized smoothing. This statement gives no hint how you should train your classifier. It tells you if you construct your classifier in this way, then you'll get this certificate. But what you know from this construction of this smooth classifier is that in inference time or at test time, it's no longer the case that your classifier will see just object-centered images, like the image is just in the center. So maybe if you're interested in rotation, deformation, you know that your classifier is gonna be evaluated on rotated versions of the image, right? Because you're pushing all of these transformed versions of the image, right? So probably one way, which was actually deployed in this paper, is just train with augmentation that matches the one that you want to certify against in test time. But again, I mean, is this the best way? Of course not. What is the best way? I don't know. It's just an open problem, because this statement just gives you no hint about it. It just tells you that if you do this, then you'll get a certificate. Like if you rechange your forward pass, then you'll get this certificate. Does that answer your question?
Yes. Thanks.
Yeah.
Yes. DNNs is relatively new area, maybe 10 years old, but for example, cluster methods, they exist 40 years, but I do not remember that I heard about random perturbation and certification of cluster algorithm or support vector machines or decision trees.
I mean,
how much you took from there?
The good thing is that for clustering methods, you can derive the actual certificate. And we did that in our work, in one of our works. So for clustering based classifiers that you classify, for example, based on nearest neighbors, then you can get like a good certificate. But the problem of these certificates is that they're always dependent on the Lipschitz constant. Suppose you're doing clustering algorithm, but on top of a feature space of a deep model. Then you're constrained by the Lipschitz constant of your deep model, right? And you have very little to do with controlling this Lipschitz constant during training, because you train this clustering-based classifier on top of a parameterized model, and you might get a good Lipschitz constant, might not, but depending on that Lipschitz constant, you get a certificate there. And another thing is that you can also take this clustering-based method, because it's a function, a classifier that outputs in a probability simplex, and you can just push it through randomized smoothing, because we made no assumptions on F. F could be a clustering-based classifier, right? And you can still get this certificate. The third nice property, I mean, of this certificate is that this certificate is typed. So once you get outside this region defined by this certificate, you're guaranteed to find an adversary just outside this region.
Sorry, it's brought me to the next question. Does it mean that certification of different methods is also different? Yes, and it could be very easy or very difficult.
Of course, like, so the point is that, I mean, randomized smoothing gives you one way to certify a given model. You could come up with a different way. I mean, the literature actually has many, many ways of certifying. Why did we talk about randomized? Like at the beginning, we showed the first slide where you could actually compute this region and propagate it through networks, which is like a method called interval bound propagation, the first slide, right? Which we showed that it is not scalable for deep models, but that's another method. And like the literature is full of lots of methods of doing certification, and different methods could lead to different certificates. The problem is that you want both to have meaningful certificate that is tight and also scalable to real world problems. But of course, I mean, different methods will lead to different certificates. Yeah.
Thank you.
Any other questions? All good? Okay. So we're here. Yeah. I mean, we're almost there. So what have we seen so far is that we're able to certify image deformations. So we have an input image, we called it X, right? And then we had a vector field P that represents pixel locations, and we perturbed this vector field by some parameterized function V with parameters phi, and we constructed the smooth classifier, right? But is this the only application? I mean, is image classification the end of the world? Of course not. We deploy similar formulation, but in another problem, which is point cloud classifications. So instead of having a camera, now we have a LiDAR or another sensor that gets you a 3D representation of some certain category, certain shape. And how would that look like? And to see how could we specialize this formulation to several applications, we just show one example here. And I'm happy to discuss in offline how could we actually specialize it to lots of or a variety of applications, and we still get this certificate or certified robustness properties. So we had this formulation, right, which we call deform RS, just randomized smoothing for deformation. And we had two annoying parts in this just due to the image classification problem. The first thing is that we have pixel intensities. And in other domains, maybe you don't really care about RGB colors, right? You just have an input that doesn't have RGB colors. An example for that is point cloud classifications, where you could just care about the shape, so you don't care about the point color, the RGB color. So we could get rid of it. The other thing is the interpolation function, and that was also constrained by the nature we constructed the images, because we said that image locations are integers, and then we cannot shift a pixel location to be between two pixels. So probably we need to interpolate between these two pixels. But in point cloud classification, for example, the space is continuous. A point could exist in anywhere. So we don't need these two annoying parts. So in point cloud models, for example, they work on a continuous space of locations, and they don't leverage color information. So you don't need these two parts. And this is what this the deform RS could be specialized for, which is a simple expectation that works on top of just locations, which is P, and this P is perturbed by this parameterizable nice deformation function, right? And to see how that goes diagrammatically, if you have a point cloud of a plane, we call it P, then this classifier will just rotate this P with different angles. You have all of these, and then you can actually push it through whatever point cloud that you're interested in certifying, and you compute this expression. And then we could deploy exactly the same result that we got from the previous deform RS, because it's just a special case of that. And we could certify point cloud classification models against meaningful deformations, right? And like the main target of this slide is not to showcase one paper or one extra work or whatnot. It's just to show that this formulation is really versatile. So you can literally just specialize it to the application you're interested in providing theoretical guarantees for, right? And yeah, I mean, so that's mostly it for the part where actually, in summary, what we have seen so far is that we saw how can we get isotropic certification via randomized smoothing. We also showed how can we get anisotropic certification, and the method was called answer right there. And we also showed how can we certify more realistic perturbations, such as deformations, via this deformer S. And we also showed one example of specializing any of these formulations to another application that is completely away from what we are interested in at the beginning of the presentation, which is called 3D deformer S, which is certifying 3D point clouds. But I mean, so far we worked with very simple setups, right? So the first setup that we worked was just input additive perturbations. The second setup was a little bit more realistic, but still not that realistic, which is just deformation with some interpolation function, because who's going to interpolate for you a rotated image and so on. So the question is, can we certify more realistic transformations? And that's going to be covered like right after lunch, I guess, according to the schedule. So if you have any questions, I'm more than happy to take it, or any side discussions, perhaps. Yeah, go ahead.
Okay, small question. Yes, I'm surprised that you started with Gaussian random noise. I would, let's say we classify dogs and cats. I would take if we want dog, I would take a cat, compute low frequency or high frequency of cat and scale it and add to all dogs. And so I will try to fake predictor.
Mm-hmm.
So why you started with Gaussian noise? It was
no, I mean, at the beginning it wasn't Gaussian. Like what was the presentation was just input additive noise. That could be anything. The way we certified, the way we constructed our smooth classifier was via deploying Gaussian distribution. But that noise that we were certifying is just any additive input perturbation, right? So if we just go back to any of the certification slides, yeah, something like this. So this certificate has nothing to do with Gaussian noise, right? It's just a quantity. You estimate this quantity, and then you're certified against additive perturbations with this quantity. But the way you actually got this quantity is via deploying Gaussian noise, right? Up there, here, like this distribution could be either Gaussian or uniform.
okay,
But,
thank you.
but the question is that if you want to do, for example, image morphing or whatnot, the problem that we have is that we don't know what makes a cat a cat. So there's no mathematical formulation that you can input a ground truth labeling function. So you give it an image, it tells you this is an image of a cat. So we don't have a mathematical description that describe categories in images. So that's why we said, okay, let's take it a little bit simpler scenario. Let's say that the class will not change, and we'll just add some semantic perturbations. I don't know. We add eyeglasses, we make the person smile, and so on. We still don't have a mathematical formulation how to describe a change in an image of a smiling person. So if you have an image of a person and an image of the same exact person but smiles, we cannot describe that mathematically, like a general mathematical formulation, right? So we said, okay, let's take that one simpler step and certify, I don't know, rotations and translations, so on, that we could actually work on top of them in some simple mathematical formulations, right? Because we know if I give you like a rotation angle, you know what to do to rotate this image, right? Regardless of this image. So then we could actually provide some meaningful certificate in terms of semantics or in terms of like actual visual content. And before that, actually, before certification, before this work, actually, like certifying these simple transformations is also a very challenging problem. And that's why people actually stepped back a little bit, said, okay, let's work with the simplest mathematical formulation. Just input, add some noise. And in this very simple mathematical formulation, they found that deep neural networks fail miserably. And I mean by miserably, you could have your perfect classifier having like, I don't know, in one of these data sets that I was just showing. I mean, yeah, here. For example, in Cypher 10, I mean, you could train a model to obtain something like 97% test accuracy, which is almost perfect, almost a human being, right? And then when very small input additive perturbation, you could drop that to absolute zero. So you could actually drop the performance of the model to make mistakes on every single input image. And this is when people started actually trying to understand the behavior of this problem, building models that are robust and so on. Like the target is there, which is certifying actual categories in terms of semantics, but I don't think we're there in terms of mathematical formulation that represents these semantic transformations.
Thank you very much.
Yeah.
Well, hi here, Sebastian. I'm remotely. Thank you very much for this nice discussion on the randomized smoothing idea. Based on Alex's question from earlier, just to make sure I understood it correctly. So, randomized smoothing, you are effectively in the basic setting with additive noise. You end up having a convolution, so you're modifying your classifier, hence being Lipschitz, and you have all these nice properties. So the naive idea would then be, okay, can't we just train, let's say, naively a network under additional like, let's say, a deep neural network under conditional constraints such that we have a certain bound on the Lipschitz constant?
So actually, this is a very nice question. So before randomized smoothing, there exists a method called Parseval network, which is basically it's very complicated to estimate the Lipschitz constant of the whole network tightly, right? Because you have like, I don't know, a composition of several layers. So if your classifier is just a linear classifier, then you have a closed form formula how to estimate the Lipschitz constant. Then maybe you could regularize it during training. If you have like a couple of layers, like some linear, some non-linearity, another linear layer, you could work the math out. But what happens in a very nasty and complicated architectures like ResNet, or I don't know, if the architecture goes beyond 10 or 20 or 50 layers, then estimating a tight Lipschitz constant mathematically becomes a very challenging problem. If you could do that, like if you have a model that performs really well on some task, and you can estimate this Lipschitz constant tightly, then probably you could just get the certificate via that theorem of the Lipschitz classifiers, deploy it there, and regularize your Lipschitz constant. Then you no longer need the smooth classifier. The bigger story is that like randomized smoothing brings to you a very simple way of estimating this Lipschitz constant tightly for any architecture. But it comes at the expense of doing a very expensive forward pass. Does that answer your question?
Yeah, partly. I was just thinking that, I mean, in randomized smoothing, you need to make this kind of noise hypotheses, right? And then, of course, you get the corresponding Lipschitz constants. But maybe if I could put a constraint on my train directly, where I only have a constraint on the Lipschitz constant, maybe I'm more flexible and I effectively allow more different perturbations under which I'm still Lipschitz. But I understand that this in complex networks may be challenging. I was just wondering then if the advances in, let's say, algorithmic differentiation may actually still open the door to this approach. Or let's rephrase. Are you familiar with any kind of comparison for, let's say, randomized smoothing and a more or less brute force constraint optimization approach for neural networks?
It's not brute force as much as regularizations. Like the methods that try to regularize Lipschitz constants, they encourage the network to have lower Lipschitz constant, not as a brute force. Because remember, like if you make this Lipschitz constant very low, you indeed get very good certificate, but nothing guarantees that this certificate is given for a right prediction, right? So you might end up with a network with very low Lipschitz constant, very good in certified robustness, but towards wrongly classified images or wrongly classified levels. So you don't want to limit the expressiveness or like the capability of the network of learning very complicated tasks, right? Like
I agree.
Yeah.
I was just more thinking that if, let's say, Lipschitz constant between this, let's say, direct approach and a randomized smoothing approach is comparable, then do you actually consider the same kind of perturbations, or are you then somehow considering different kind of perturbations in different approaches?
I mean, they are comparable if you're able to estimate that Lipschitz constant. That's my take on it.
Okay, thanks.
Yeah. But earlier approaches didn't show any successful attempts of regularizing Lipschitz constant and building both accurate and robust model.
I see. Okay,
right.
Thank you.
Welcome. Yeah. Just throw it.
Thanks. So I have questions about your certification, because at the end you certificate the expected value.
Can you?
At the end, you certificate the expected values of a function, right?
Yeah, my certificate actually needs an estimate of some expected value, yes, which is this probabilities. I mean, let's get to the simplest form of this certificate, which is somewhere here, right? Yeah, which is Didn't work. I mean, yeah. So like you need to estimate these two probabilities, which are outputs of some expected value. Yeah.
And so if you go forward some slide to your
Forward or
theorem,
backward?
to your theorems, theorem 1. I think so.
This one?
The theorem 1.
I think it is. Yeah. Like again, if you build a smooth classifier, like this is also, I mean, this is also controlled by how you're doing the forward pass through G through your classifier. So if your forward pass through G is just a single forward pass, like if you build a model that is Lipschitz, and your Lipschitz constant is very small, you're happy with it, and the forward pass is estimated cheaply, and you just do this cheap forward pass, estimate this top two probabilities, right? G of CA and the runner-up class. And then you substitute in this formula, you get your certified radius.
So my question is that you have, so I do not remember exactly slide, but you say that expected values when you have your map apply on inputs plus some noise.
Yes.
So noise following some distribution. So the outputs will be some distribution, and you certificate the expected value of the output.
Yeah, you certify the smooth classifier, which is this expectation formula. Yeah.
So so it means that when I put the noise follows a distribution, I have distribution of the output. It does anyway we can get more information about the distribution of output.
Well, can you rephrase or just also raise your voice?
So so you see your epsilons following some Gaussian distribution.
Or uniform later on. Yeah, yeah. It follows any distribution. Yeah.
So now you take x plus epsilon. You will get some y depend on sample epsilon.
Yeah, so each x plus epsilon follows the same distribution, but with a shifted mean, because we assumed zero mean distributions.
Yeah. And then you get the expected value of y. Right?
Yes.
My question is that can we get some more information about the distribution of y?
I mean, yeah, again, so, okay. That's a very nice question, actually. So let's get back again to the early definition of randomized smoothing. Yeah, any of these lines. So we have g of x is just this expectation, right? If you're able to have a closed form of this expectation, then you no longer have this Monte Carlo. You no longer have to do all of these forward passes to estimate this expectation. Suppose your f is just a linear model. Then you know how to estimate this, like in a closed form, and then you just substitute that in the PA and PB. You no longer need to estimate it. The problem is that with deep models, like it is very, very complicated to estimate a closed form for this expectation. But if you're able to do so, then yeah, I mean, that would be amazing. It's just you mitigated the main drawback of randomized smoothing.
Thanks.
Yeah.
I apologize if this question is very trivial, but because I don't work on neural networks. But I want to ask about, so when you do this perturbations, so are there any things in those regions that you don't want? Because I'm thinking for the images that Eric showed yesterday about the dogs and the muffins. And this, it seems that if you change a little bit, you might have something that's absolutely different. So I'm wondering what kind of, what is the domain that when you discuss the domain of your pictures, what are the content of your domain? Also, what, so the norm, when you say the L2 norm, seems to me that it is too weak of a norm because you might, maybe a sort of norm might be more reasonable to me.
So you say how meaningful does this circuit is?
No, I'm asking. I'm just asking if you could explain to me what is the domain, the domain of your pictures. Do you understand?
And you want to certify against those?
Yeah.
Yeah, but
those two questions actually. Yeah, it's the basic question. It's not about certification.
Yeah. So yeah, I mean, I mean, the problem, like, it's not a problem actually. Like this result is generic. I mean, you could construct your perturbation the way you want, as long as this inequality is satisfied.
No, if you go, for example, in the slide where you have C1 region and C2 region, and you have the F function.
Yes, something like this slide.
Yes. So on the left side, what is this domain? What does it contain? Sorry.
I mean, it's just all points that belongs to a different class.
Yes. Okay.
So
this is just a diagram to give the idea.
yeah, I mean, you could say that C1 is just all images of cats and C2 all images of dogs. Right? I mean, all images that the network thinks that they are cats, and C2 are all, like the points here, are all images that the network thinks that they are dogs.
Why are you perturbing if you?
No, but I mean, it's not necessarily the case, because we know that, for example, if my image is here, then all of these images, they look exactly as a cat, right? It's just some noise added to the cat. So why does the network think that this point, despite its closeness to X, is a dog, which is an undesirable property, like? So what we really want is that all images that look to us as cats, still the network recognizes them as cats. Does that answer your question? Any other questions?
And the other question: why the L2 norm? Why is not a simple?
I mean, so we had to start with something. So people started with just additive perturbations subject to some norm, because this is the simplest thing that we could actually work out the math with. Because with L2 norms, you can derive the projection. You can, I don't know, have some interpretable meaning, like it's an energy or something. But if your application requests certificate against other norms, then yeah, I mean, then you need to certify other norms. And we saw how to certify other norms in this anisotropic certification. Yeah,
I have just a clarification. Like, can we go back to a table of results where we compared the two different data sets with CFR10?
Yes.
So just the correct interpretation of that is that, okay, this is like, there was R of rotation of 30 degrees and then 10 for a CFR10, if I remember correctly.
Let me get to that just to fully understand your question. So you mean this table?
Here.
Yes.
So basically this values of, like, for example, rotation 30, it's like, is it correct that if we have, like, this is a maximum number of degrees that we can rotate so that we have a certification guarantee?
Yes.
And like, if we go just like 31 degrees, then this is
There exists an adversary.
Okay.
Well, I mean, because 31 degrees could be in this direction or this direction. We don't know. For example, in the input additive perturbation, it's like a ball.
Right.
It just says that once you step outside this ball, I am not responsible if the system fails. I can give you an insurance that the system will not fail in this region. But yeah, that's true.
So let's keep it. If there's just one last question, we can do that and then goes to lunch. Is there one more question anyone wants to ask?
Last question. Yeah.
Yeah, this is the one in the corner.
Can you throw just the mic?
Regarding the last question also, when you generate your perturbations, for example, for this 30 angle deviation from the image, let's say, do your samples, I mean, perturb larger than 30%?
Can you repeat that?
I mean, are your all perturbations inside the 30% region, or do you have also samples that go beyond this?
I mean, like when you do inference, when you sample.
When you sample.
Yeah, so I mean, it depends. Like, for example, if you choose Gaussian distribution, then you cannot actually guarantee anything. You can end up in a rotated image with, I don't know, 300 degrees.
But for that samples, you don't have like a guarantee.
No, I mean, it depends. So it depends. Is it during inference time or the region in which you give insurance or you certify your classifier against? So during inference time depends on the distribution. But in any case, this is the region on which adversaries cannot exist. But it should be like contained within this region. So if if the perturbation is actually outside this region, then maybe there's an adversary.
Okay, so this angle only, actually depends on how Lipschitz your function is, right? In the end.
Yeah. So again,
okay.
So I'm not saying that the certified accuracy at 31 degrees is going to be 0.
Okay. Yeah.
No, but it's not going to be 96.8 anymore. You want to check then how many samples, if you were to compute the certified radius, like that formula, is going to give you something that is larger than 31 degrees. And then you see what percentage of your test set satisfies this criterion, and this is going to be your certified accuracy. So for example, if 50% of your samples have, I don't know, like if you compute the certified radius is going to be at least 50 degrees, then your certified accuracy is going to be 50% at radius of 50.
Yeah, thanks.
Yeah, no worries.
Okay, so let's conclude this morning session, and let's thank both speakers. Thank you very much. So we resume after lunch at 2 p.m. in this room. Thank you.